Long before the first star sputtered to life, and before the first galaxy started its slow, cosmic ballet, the universe wasn't what you might expect. It wasn't a vast, cold emptiness. Instead, try to picture an endless, silent fog. A fog that wasn't damp or chilly, but glowed with a uniform, searing heat. There were no places to go, no points of light in a dark sky, because there was no dark sky. There was only light, everywhere, trapped inside a universe that was smaller, simpler, and smoother than it would ever be again. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. In this story, we're not looking for stars or galaxies. We're traveling back to a time before they were even possible. We're going in search of the first, faint ripples in that primordial calm. We're looking for the blueprint of the cosmos itself, a pattern that is both the oldest and the largest thing in our entire universe. So get comfortable, as we drift back through the eons, to a time when the universe was filled not with things, but with a quiet, glowing potential. The age of light, but not of sight. When we think of the early universe, we usually picture a black, empty void just waiting for someone to flip the on switch for the stars. But that picture, as dramatic as it is completely wrong. The beginning wasn't dark, it was blindingly bright. For hundreds of thousands of years after the Big Bang, the entire cosmos was filled with a brilliant, opaque fog of plasma. To get a handle on this, let's picture the universe shortly after its initial, explosive expansion. It was unbelievably hot and dense. So hot, that the basic building blocks of matter couldn't get their act together. The universe was a seething soup of fundamental particles, mostly a chaotic mix of protons and zippy, energetic electrons. In this environment, they were all free, unbound, just a sea of electric charge. This state of matter, a superheated gas where electrons are stripped away from their atoms, is called a plasma. You've actually seen it before, even if you didn't know the name. The heart of our sun is a plasma. A bolt of lightning creates a channel of plasma right through the air. The glow inside a fluorescent light bulb? That's plasma, too. Now, imagine that glowing, energetic state, but not trapped in a star or a glass tube. Imagine it filling everything. The entire observable universe was like being on the inside of a single, colossal star. The temperature was extreme, and it slowly cooled over millennia to something like the surface of a modern star a few thousand degrees. The universe would have glowed with a brilliant, uniform, yellow-white light. But here's the strange part. In this universe filled with light, you couldn't have seen a thing. It was an age of light, but not of sight. The reason it was so opaque was the plasma itself. The universe was packed with photons, the particles of light, and these photons were on a desperate but hopeless journey. They'd travel a tiny distance, only to immediately smack into one of the free-roaming electrons. Each collision would send the photon careening off in a random new direction, only to hit another electron, and another, and another. It's like being in the thickest fog you can possibly imagine. The light from a street lamp can't reach you directly. It just scatters off countless water droplets, creating a blurry, directionless glow. You know there's light, but you can't see where it's coming from. The early universe took this idea to the absolute extreme. A photon couldn't travel freely. It was trapped in an endless game of pinball, bouncing between electrons. The whole universe was a single, glowing, featureless fog. No shadows, no shapes, no forms. And this state of perfect, uniform smoothness is where our mystery begins. It was a universe with almost no features. Almost. The uniformity was nearly perfect, but not quite. Hidden in that smooth, glowing plasma were the faintest of imperfections. Tiny, almost unnoticeable variations in density and temperature differences of just 1 part in 100,000. They weren't structures yet. They were just the ghost of a possibility, the quiet promise of a universe to come. And to understand where they came from, we have to go back even further, to the very first moments of time itself. The cosmic hum. That incredible smoothness wasn't an accident. It was the direct result of something that happened in the universe's very first second, a period called cosmic inflation. In a sliver of a moment, the universe expanded at a mind-boggling rate, stretching from smaller than an atom to something astronomically huge. This process was like taking a crumpled piece of paper and stretching it out until it was perfectly flat on a massive scale. Inflation ironed out the universe, giving us that near-perfect uniformity. But in the world of the very, very small, the quantum realm, things are never truly still. It's a place of constant uncertainty, a fizzing foam of energy where particles pop in and out of existence. During that incredible period of stretching, these microscopic quantum jitters in the fabric of spacetime itself were also stretched. What were once unimaginably small variations were blown up to astronomical size. They became the seeds of all future structure. These were the tiny imperfections, those 1 in 100,000 variations, that got baked into the fabric of the cosmos. As the universe settled after inflation, it was filled with that hot, dense plasma soup. And these imprinted seeds of structure started to make themselves known. A region that was just infinitesimally denser than the areas around it had slightly more gravity. It would begin to gently pull matter, protons, electrons, and the mysterious dark matter towards it. This kicked off a great cosmic battle, a push and pull that would define the universe for the next 380,000 years. On one side, you had gravity, always pulling inward, wanting to make dense regions even denser. On the other side was pressure. The plasma wasn't just matter, it was swarming with incredibly energetic photons. When gravity tried to squeeze a region of plasma, the photons trapped inside got squeezed too. This created a huge outward pressure, like a coiled spring, that fought back against gravity's pull. So, an overdense region would start to collapse under its own gravity. But as it collapsed, the photon pressure inside would build until it became overwhelming, causing the region to violently rebound and expand. As it expanded, the pressure would drop, and gravity would take over again, starting the whole cycle over. Inward, then outward. Collapse, then rebound. This constant push and pull created huge ripples that traveled through the primordial plasma. They were, quite literally, sound waves. Not sound traveling through air, but waves of compression moving through the stuff of the early universe. For hundreds of thousands of years, the entire cosmos was ringing like a bell, filled with a deep, resonant hum. These are what we now call baryon acoustic oscillations, or BAO. The baryon part just refers to the ordinary matter, like protons, that was being carried along for the ride. Imagine dropping a pebble into a perfectly still pond. Ripples spread out in a perfect circle. In the early universe, it was as if countless pebbles were dropped everywhere at once. Each tiny, quantum-seeded overdensity was the center of its own spherical sound wave, expanding out into the plasma at more than half the speed of light. But they didn't travel forever. They traveled for as long as the universe was a plasma, as long as the light was trapped in the cosmic fog. The biggest of these sound waves, the ones that had been traveling for that entire 380,000 year period, reached a very specific size. They traveled a certain distance from where they started, and then, suddenly, they stopped. The universe was about to change completely. The cosmic hum was about to fade, and the pattern frozen in place by these sound waves would become the first, and largest, structure we can ever hope to see. The Great Liberation. For 380,000 years, the universe was a glowing, opaque fog, ringing with cosmic sound waves. All the while, it kept expanding and cooling. The relentless heat that kept atoms from forming was slowly fading. The cosmos was getting close to a tipping point that would change everything. That moment arrived when the temperature of the universe dropped to about 3,000 Kelvin, roughly the surface temperature of a red giant star. That still sounds incredibly hot, but for the chaotic dance of protons and electrons, it was a moment of calm. At this temperature, the photons had lost just enough energy. They weren't powerful enough anymore to instantly knock an electron away from a proton. For the very first time, the pull between a positive proton and a negative electron could win. And so, all across the cosmos at once, an event called recombination began. Electrons and protons started binding together, forming the first stable, neutral atoms of hydrogen. The effect of this was immediate and profound. Remember, the universe was opaque because photons were constantly scattering off free electrons. But now, those electrons were being captured and locked into atoms. Suddenly, a photon could travel through space and find nothing to bump into. The endless pinball game was over. The fog lifted. In a cosmological instant, the entire universe went from being an opaque, glowing plasma to being perfectly transparent. It was like a universal dawn breaking everywhere at once. The light that had been trapped and scattered for 380,000 years was finally set free. These photons began to stream across the cosmos in straight lines, carrying with them a final snapshot of the infant universe. This flood of ancient light is what we now call the cosmic microwave background, or CMB. It's the oldest light in the universe, an echo of that primordial fireball. It's basically a baby picture of our cosmos, taken at the precise moment it became transparent. When we look at the CMB, we're looking back in time to the edge of that primordial fog, an event called the surface of last scattering. This ancient light is all around us. It fills every cubic centimeter of space. In fact, if you've ever tuned an old analog TV to a dead channel, a small percentage of that snow was interference from the cosmic microwave background photons from the dawn of time, ending their 13.8 billion year journey by hitting your TV antenna. Of course, the light isn't a brilliant yellow-white glow anymore. Over the 13.8 billion years since it was released, the universe has expanded by a factor of over 1,000. As space stretched, it stretched the wavelength of this light along with it. This cosmological redshift has stretched the once high-energy visible light so much that it's now in the microwave part of the spectrum. Its fiery 3,000 Kelvin temperature has cooled to a mere 2,725 Kelvin, just under 3 degrees above absolute zero. That's why we need sensitive radio telescopes to see it. And when we do, we find something remarkable. We see a near perfectly uniform glow coming from every direction. It carries the secrets of the universe's beginning, and encoded in its faint temperature, in tiny variations, is the answer to our question. It is the oldest and largest structure in the universe. The oldest structure revealed. To finally see this structure, we have to look at the sky with the tools of modern cosmology. The story of its discovery began by accident in 1964. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large antenna for Bell Labs and were frustrated by a faint, persistent background noise. It came from every direction, day and night, no matter where they pointed the antenna. They even cleaned out pigeon droppings from inside of it, thinking that might be the source. It wasn't. At the same time, just a few miles away at Princeton University, a team of physicists was building an experiment to find the very thing Penzias and Wilson had stumbled upon, the predicted afterglow of the Big Bang. When the two groups connected, they realized the annoying hiss in the Bell Labs antenna was nothing less than the sound of creation. Penzias and Wilson had found the cosmic microwave background, and they would win the Nobel Prize for it in 1978. But their discovery only showed a smooth background. Seeing the true structure hidden inside it would take decades and a series of powerful space observatories, NASA's COBE, WMAP, and the European Space Agency's Planck satellite. What they revealed was breathtaking. They created an all-sky map of the CMB's temperature and found a canvas of stunning complexity. Against the nearly uniform 725K background, there were tiny fluctuations, subtle patches of slightly warmer and colder regions. These are the structure we've been looking for. The faint red and blue spots on the map are a direct photograph of the sound waves that were rippling through the plasma 8 billion years ago. They are the baryon acoustic oscillations, frozen in time. The slightly hotter, red spots are regions where the plasma was a bit less dense. The slightly colder, blue spots are where it was a bit denser, where gravity was just starting to win its fight. These temperature differences are minuscule, differing from the average by only about 1 part in 100,000, but they are the blueprint for everything that exists today. So, how big is this structure? Well, the answer comes in 2 parts. First, the oldest structure is the entire pattern itself, a single, coherent web of ripples spread across the whole observable universe. But within that pattern, the most prominent ripples have a specific size. This size is set by the maximum distance a sound wave could travel in those first 380,000 years. After 8 billion years of cosmic expansion, that distance has been stretched to a diameter of about 490 million light-years. This is the sound horizon, and it's an immense cosmic measuring stick. Second, there are specific, individual features in the CMB map that are truly colossal. The most famous is the CMB cold spot. It's a region of the sky in the direction of the constellation Eridanus that is unusually large and unusually cold. This patch is about 70 microkelvin colder than average, with its deepest parts dropping 140 microkelvin colder. It stretches across an area of the sky about 20 times the width of the full moon. At its vast distance, that translates to a physical diameter of roughly 8 billion light-years. One leading theory suggests it might be an illusion caused by a gigantic supervoid, an enormous, unusually empty region of space that lies between us and the CMB. But even if it's a supervoid, it would still be one of the largest known structures in the universe, its effect permanently stamped on the oldest light. Many studies suggest the void isn't big enough to explain the entire effect, leaving open the incredible possibility that the cold spot is a genuine, primordial giant, one of the very first and largest seeds of structure in the entire cosmos. From ripples to reality, those faint whispers in the cosmic dawn, those tiny temperature variations, didn't stay whispers for long. They were the starting pistol for the next phase of cosmic history. Once the universe became transparent and the photons streamed away, the outward pressure that had been fighting gravity was gone. Now, gravity had no opposition. The stage was set.
Across the universe, the slightly denser, slightly cooler blue spots on the CMB map had the upper hand. They had a tiny bit more matter and a little more gravitational pull. And over cosmic history, a tiny advantage is all you need. Slowly but surely, these regions began to pull in more and more matter. For millions of years, it was just a quiet gathering of cosmic gas in the dark. But as the density grew, so did the gravity, pulling in material at an ever faster rate. Finally, hundreds of millions of years after the CMB's light was released, the gas in the hearts of these collapsing clouds became so dense and so hot that a new fire was ignited: nuclear fusion. The first stars blinked on, bathing the universe in a new kind of light, forged from the very matter the primordial ripples had gathered. These first stars were born inside the gravitational wells carved out by the cold spots of the CMB. The warmer, less dense red spots on the map lost out. They became the great cosmic voids, the vast empty expanses between the great structures of the universe. The stars gathered into the first galaxies. Those galaxies, following the same gravitational blueprint, were drawn together into galaxy clusters. And the clusters were strung along vast, interconnected tendrils of matter, forming the magnificent, universe-spanning cosmic web. The shimmering filaments and dense knots of this web are the direct descendants of the cold spots in the CMB. The empty voids between them are the legacy of the hot spots. Every galaxy, every star, every planet, and yes, every atom in your body, can trace its origin back to this process. The material that makes up our world was once part of that primordial plasma, pulled together by the gravity of a faint, cold ripple in a 13.8 billion-year-old sea of light. We are, in the most profound sense, the products of the oldest structure in the universe. When we look up at the night sky, we see the light of stars and galaxies. But the most profound light is the one we can't see with our eyes. It's a faint, cold glow that comes from every direction at once. It's the afterglow of a time before a single star had ever shone. This light, the cosmic microwave background, carries the image of the universe's very first structure. Not a structure of rock or gas, but one of pure potential. A pattern of unimaginably vast ripples, born from the battle between gravity and light, that dwarf any galaxy cluster. The universe wasn't born in pure chaos. It began its life in a state of near-perfect calm, with a deep, resonant hum. From that hum, a blueprint was frozen into space-time, a blueprint that told matter where to gather and where to spread out. From those first faint ripples, everything we see, and everything we are, would eventually grow. The largest structure in the universe is also its oldest memory, a silent, beautiful testament to a calm, cosmic beginning. If you enjoyed this journey into the quiet corners of our universe, consider subscribing for more explorations into the cosmos. Part 2, The First Tiny Irregularities. If the early universe had been truly perfect, completely smooth in every direction, nothing much would have happened. It would have expanded, cooled, and drifted into a kind of quiet emptiness. No stars, no galaxies, no planets, no night sky. No one, billions of years later, looking up and wondering how any of it began. That is one of the strangest things about the cosmos. Everything beautiful in it seems to depend on the fact that it was never quite perfect. After the universe became transparent, after the great glowing fog lifted and the oldest light was finally set free, what remained was a cosmos that looked astonishingly uniform. If you could have somehow floated there in those distant ages, you would not have seen grand structures or glowing islands of stars. You would have seen darkness. A vast, expanding darkness filled mostly with hydrogen and helium gas, and threaded through it all, the invisible presence of dark matter. It was a simple universe. Calm, young, almost featureless. But only almost. Buried inside that calm were tiny irregularities. Slight differences in density. Slight differences in temperature. Slight differences in how matter was distributed from place to place. The variations were unbelievably small, just a whisper of imbalance in a universe that was otherwise nearly smooth. And yet those tiny irregularities were not minor details. They were the whole story in miniature. They were the reason the universe would one day have structure at all. It helps to imagine a perfectly flat plain after fresh snow. At first glance, it looks level and undisturbed. But if you look closely enough, you might notice the faintest dips and rises. A shallow hollow here. A gentle ridge there. If the wind begins to move, snow will gather a little more easily in the hollows. The dips deepen. The ridges sharpen. A tiny advantage becomes a visible pattern. The early universe worked in a similar way. Gravity noticed what the eye could barely detect. The smallest overdense region, a place with just a little more matter than average, had a tiny extra pull. Not much. Not enough to create anything dramatic at first. But gravity is patient in a way almost nothing else is. It does not rush. It does not tire. Give it a slight unevenness and enough time, and it will build worlds. The question, then, is where those Venices came from. To answer that, we have to go back even earlier than the hot plasma and the first released light. We have to go back to a universe so young that words like star, galaxy, or even atom would have meant nothing. We have to go back to a time when reality itself may have been trembling. The leading scientific picture begins with a period called inflation, a phase in which the universe expanded at a staggering rate in an incredibly tiny fraction of a second. It is difficult to overstate how violent and strange that idea is. We are not talking about matter flying through space, the way debris flies outward after an explosion. We are talking about space itself stretching. Distances that had once been unimaginably tiny were pulled apart faster than intuition can comfortably follow. And in that strange moment, the smallest flickers of the quantum world may have been enlarged into cosmic size. The quantum world is not smooth or still. Even in what we casually call empty space, there is a kind of restless uncertainty. Tiny fluctuations appear and disappear. Energy shifts. Fields tremble. It is less like a quiet floor and more like the faint shimmer on the surface of water, except happening at scales so small that ordinary experience offers no good comparison. Under normal conditions, those fluctuations remain microscopic. They flicker below the level of anything familiar. But inflation, if it happened the way physicists think it did, acted like an incredible magnifier. It took those almost meaningless quantum jitters and stretched them across the young universe. In a sense, the cosmos inherited its large-scale unevenness from the smallest possible restlessness. That idea is so elegant it almost sounds fictional. The largest structures in existence may owe their origin to microscopic uncertainty. The great galaxies, the cosmic web, the enormous walls of matter stretching across space, may all descend from tiny fluctuations in the earliest instants of time. There is something almost poetic in that. The universe was not built in spite of uncertainty. It may have been built because of it. Once inflation ended, the universe continued to expand and cool, but it now carried within it those faint imprints. Matter was not distributed with total perfection. Some regions were ever so slightly denser. Others were ever so slightly thinner. At first, the differences were laughably small. If you had tried to measure them with ordinary human instincts, you would have called the universe uniform and left it at that. But nature is not limited by human instincts. Gravity can work with subtleties we would miss entirely. Still, in those first hundreds of thousands of years, gravity could not simply pull matter inward without resistance. Ordinary matter was tightly coupled to radiation in that hot plasma phase. Light and matter kept interacting, pushing and pulling, smoothing and scattering. The universe had the seeds of structure, but the seeds had not yet broken through the soil. Only later, once neutral atoms formed and the light decoupled, did the story begin to shift. The pressure from radiation weakened. The universe became transparent. The ancient glow streamed outward. And now those slight irregularities had a different future in front of them. The overdense regions had a little more mass, and therefore a little more gravitational influence. So they began, very slowly, to gather more material. The underdense regions had slightly less, so matter was a little less likely to remain there. The universe was not changing all at once. It was not a dramatic transformation. It was more like watching frost spread across a window in almost imperceptible steps. If you stared at any single moment, it would seem still. Only over long stretches would the pattern reveal itself. This is one of the hardest things to emotionally grasp about cosmology. We are used to motion that can be seen. Falling rain, running rivers, clouds moving across the sky. But the early universe evolved on timescales that make human urgency feel almost absurd. Millions of years could pass while the cosmos was still only preparing its first visible structures. The irregularities were there, but they were growing in silence. And the silence mattered. There is a name often given to the era after the cosmic microwave background was released but before the first stars lit up. It is called the cosmic dark ages. That sounds dramatic, but in a calm way it is exactly right. The universe had gone dark. The great fog was gone. The first stars were not yet shining. The matter was there, the seeds were there, gravity was at work, but the cosmos had not yet begun to sparkle. If you had floated through that age, it would have been a place of deep darkness and slow preparation, a universe waiting on its own future. And underneath that darkness, the tiny irregularities were quietly taking on more importance with every passing age. It is useful here to think about interest accumulating in a bank account, though on an unimaginably slower and grander scale. A small deposit, left untouched, can grow. Not because anything flashy happens in a day, but because the gain compounds over time. In the same way, a slightly denser patch of matter did not need to be dramatically different at the start. It only needed a tiny edge, because that edge would slowly reinforce itself. The denser patch attracted more matter, which made it denser still, which increased its pull, which drew in more matter again. This is one of gravity's most powerful habits. It rewards imbalance. Of course, the universe was still expanding, and expansion matters. It worked against collapse on the largest scales, stretching space and making it harder for gravity to gather material quickly. So the story of the first irregularities is not simply gravity winning immediately. It is a delicate contest between expansion and attraction, smoothness and clumping, patience and persistence. Some irregularities were too small to matter much at first. Some were washed out or grew only weakly. Others, especially where dark matter played its quiet role, became the foundation for everything that came later. Dark matter is difficult to avoid in this story, even before we fully arrive at it. It does not shine. It does not reflect light. It does not seem to interact much with ordinary matter except through gravity. And yet it appears to make up most of the matter in the universe. That means the early universe was not mainly shaped by the visible atoms we are familiar with, but by a vast invisible component. Ordinary matter, in those earliest times, had been tangled up with radiation. Dark matter was freer. It did not feel the same pressure from light. So while ordinary matter was still being jostled and smoothed out by the hot early cosmos, dark matter could begin building its own subtle scaffolding. Not stars. Not glowing clouds. Just gravitational structure. Hidden wells in the landscape. Invisible architecture waiting for ordinary matter to fall into it later. But for now, in this part of the story, what matters most is the principle itself. The universe did not move from chaos to order in one dramatic leap. It moved from near smoothness to slight unevenness, and from slight unevenness to the possibility of future structure. Before there were galaxies, there were preferences. Before there were clusters, there were tendencies. Before there were cosmic walls and bright spiral disks, there were tiny regions where matter was just a little more likely to gather than elsewhere. That is how much of reality begins. Not with a bang in the ordinary sense, but with a bias. And when you think about it, that may be one of the most reassuring patterns in nature. Vast outcomes often come from almost invisible beginnings. Mountains are shaped by countless drops of rain. Forests begin from fragile seeds. Human lives can turn on quiet decisions that seemed small at the time. The cosmos, in its own way, followed that pattern too. Its grandest architecture began in irregularities so tiny they barely deserved the name. When cosmologists map the microwave background, those little temperature variations are often shown in bright colors. Blues and reds. Cool and warm patches. But those images can make the early universe seem more dramatic than it really was. The actual differences were tiny beyond ordinary comprehension. The maps are exaggerated so we can see them at all. In reality, the infant cosmos was astonishingly smooth, which makes the outcome even more remarkable. It is as if the universe built cathedrals out of ripples. And maybe that is why this stage of the story feels so important. It reminds us that the oldest structure was not a structure in the familiar sense. It was not a tower of matter or a shining wheel of stars. It was a pattern of slight irregularity, stretched across a young universe, a cosmic tendency, a map of where things might slowly begin to happen. This is also where the topic becomes quietly philosophical, even if we stay grounded in science. We often think perfection is the highest state, perfect symmetry, perfect balance, perfect smoothness. But a perfectly smooth universe would have remained empty of complexity. It was imperfection that allowed the cosmos to become interesting. Tiny departures from sameness made history possible. In that sense, the first irregularities were not flaws in creation. They were the beginning of form, the beginning of memory, the beginning of everything the universe would someday become. And yet, at this point in the story, none of that future splendor was visible. No galaxy had yet formed. No star had burned. No heavy elements had been forged in stellar hearts. The universe still held its wonders in secret. It was carrying the instructions, not yet the finished design. There is something peaceful about that image. A dark universe, calm and almost empty to the eye, but quietly rich with possibility. The blueprint already present, though nothing obvious had been built from it yet. If you have ever planted something and then stared at the soil the next day, you know the feeling. Nothing seems to have changed. The surface is still. The pot looks empty. But beneath it, hidden from view, processes are underway. Moisture is moving. Cells are dividing. A direction has been chosen. The future plant is already there in tendency, though not yet in form. That was the universe in the age of its first tiny irregularities. Not empty, not inactive, just hidden. Over immense spans of time, those hidden differences would deepen. Gravity would continue its patient work. Dark matter would gather first, more confidently than ordinary matter. Gas would begin to fall into invisible wells. The first true structures would begin to emerge from what had once looked like almost nothing at all. And when that happened, the universe would cross a threshold. It would move from subtle unevenness to actual architecture, from suggestion to shape, from blueprint to scaffolding. That next step belongs to the invisible giants that formed before the first galaxies could truly take hold. Before we go there, though, it is worth lingering for one quiet moment longer with this truth. The cosmos did not need grand differences to begin building itself. It only needed tiny ones. A slight excess here, a slight deficit there, a soft departure from perfect smoothness. That was enough. Enough for gravity to notice. Enough for history to start unfolding. Enough, eventually, for stars to be born, galaxies to turn, planets to gather, oceans to form, and minds like ours to appear inside the story and wonder how the whole thing ever began. And if you enjoy these slow journeys through the quiet beginnings of the universe, you can always support the channel with a gentle like or subscribe. And if you feel like it, leave a comment about where in the world you're listening from tonight. There is something fitting about many small points of awareness gathering around one old cosmic question. For now, though, the universe is still dark. The first visible lights have not arrived. The matter is still learning where to go. But the invisible framework is beginning to take shape. That is where we go next. Part 3: The invisible structures that formed first. If you had drifted through the universe in its long dark youth, you would have seen almost nothing at all. No stars burning in the distance. No galaxies turning slowly in the black. No glowing clouds. No familiar shapes. Just an immense darkness, stretched across every direction, with matter spread thinly through it and time moving in patient silence. It would have seemed empty, almost uneventful, as if the cosmos were still undecided about whether it wanted to become anything more. And yet, beneath that quiet surface, something enormous was already beginning. Long before the first star lit up, long before the first galaxy gathered itself into a visible island of light, The universe had already started building structure. Not bright structure. Not anything an eye could easily admire. The first architecture of the cosmos was invisible. It was made not of shining gas, but of dark matter, gathering itself into vast gravitational shapes that no one could see, but that everything else would one day follow. This is one of the most important and strangely beautiful ideas in modern cosmology. The universe did not begin by making stars. First, it made shadows. It made hidden wells in the landscape of space, invisible valleys where future matter would slowly collect. Before the luminous universe could exist, the dark one had to prepare the ground. That may sound dramatic, but in truth it happened with extraordinary calm. In the last part, we lingered with the first tiny irregularities, those faint differences in density left behind by the earliest moments of cosmic history. They were so small that the young universe still looked almost perfectly smooth. But gravity does not need bold differences. It only needs enough to begin. A slightly denser region could pull a little more strongly than its surroundings. A tiny advantage could deepen over time. And with enough patience, that was all the universe required. But ordinary matter, the kind made of protons, electrons, and eventually atoms, was not alone in that story. In fact, it was not even the main actor yet. Most of the matter in the universe appears to be dark matter. We still do not know exactly what it is. We know it is not ordinary atoms. It does not glow, does not absorb light in the normal way, and seems to pass through both matter and radiation with eerie indifference. We know it mostly by its gravity, by the way it bends the paths of galaxies, shapes the motions of clusters, and quietly outweighs the visible universe many times over. For a sleep channel, there is something almost soothing about dark matter's personality. It does not announce itself. It does not sparkle. It does not ask to be admired. It simply exerts its influence in silence. The universe, in a way, was first organized by something hidden. That hidden quality is what made dark matter so important in the early cosmos. Ordinary matter had a complicated beginning. Before the universe became transparent, normal matter was tightly coupled to radiation. Photons were scattering constantly, keeping the hot plasma stirred up. There was pressure. There was resistance. Ordinary matter could not simply fall inward wherever gravity wanted it to go. It was being pushed around by light itself. Dark matter, as far as we understand it, did not have to deal with that in the same way. It was not bound into that glowing fog. It did not feel the push of radiation the way ordinary matter did. So while the visible universe was still trapped in its bright, turbulent early state, dark matter was already beginning to gather more freely under the pull of gravity. That difference changed everything. Imagine two kinds of travelers crossing the same landscape. One is moving through deep water, forced to fight resistance at every step. The other is walking through clear air. Even if they begin at the same moment and head in the same direction, one will organize more quickly than the other. In the early universe, ordinary matter was the traveler wading through water. Dark matter was the one moving through stillness. So as the cosmos expanded and the first tiny irregularities began evolving, dark matter could start clumping earlier and more effectively. Not into stars, not into anything hard or familiar, but into halos. These halos were regions where dark matter gathered in roughly spherical distributions, making invisible pockets of stronger gravity. They were not solid objects. They were more like gravitational landscapes, places where the density of dark matter was higher than average, and where future structure could take root. The word halo can sound light and delicate, but these were colossal things. They were the first true gravitational homes in the universe. Empty of starlight, yes. Invisible, yes. But real. They were the earliest places where the universe began setting aside room for galaxies that did not yet exist. It helps to think of them not as objects you would touch, but as valleys in space-time. If matter were like mist drifting over a landscape, the dark matter halos were the hollows where the mist would naturally gather. The mist itself might be hard to notice at first. The valley might be invisible. But over time, the shape of the land decides where everything goes. And that is exactly what dark matter did. It shaped the land before the visible cosmos arrived. This is why the first structure in the universe was not really luminous at all. The earliest stage of cosmic architecture was gravitational rather than visual. The universe's first skeleton was built in darkness. When people imagine the beginning of cosmic history, they often picture a sequence that starts with light. First stars, first dawn, first galaxies. But in a deeper sense, dawn was not the first act. The first act was preparation. The universe first constructed a hidden framework, and only later draped it in glowing matter. That hidden framework began from the same small irregularities we talked about before. Dark matter, like ordinary matter, inherited the unevenness of the early universe. Some regions held slightly more of it than others. Those denser patches pulled inward more effectively. As the universe expanded, gravity slowly drew dark matter into clumps. The clumps grew. Small halos formed. Some merged into larger halos. Others were torn apart and absorbed by bigger structures. This process was not neat or symmetrical. It was not one grand collapse happening everywhere at once. It was more like the gradual emergence of a web of hidden density, with small structures forming first and larger ones building from them over time. In modern cosmology, this is often called hierarchical structure formation. Small things first, then larger things through merging and growth. Tiny halos became bigger halos. Bigger halos became the seeds of future galaxies and clusters. The universe did not begin by building its grandest structures outright. It began with countless modest clumps, and let time do the assembling. That is a deeply natural pattern. Rivers begin from small trickles. Cities begin from scattered dwellings. Forests begin from individual roots. Complexity often starts in fragments, then combines. The first dark matter halos may have formed surprisingly early, perhaps when the universe was still only tens of millions of years old, though the exact timing depends on their size and the details of the models. In cosmic terms, that is almost immediate. Not immediate to us, of course. Tens of millions of years would be an unimaginable age for human history. But for a universe that is roughly 13.8 billion years old, it was the beginning of the beginning. Still, even once those halos existed, the universe remained dark. This is important to linger on, because it keeps the mood of the era honest. Nothing suddenly became bright just because the scaffolding was there. The halos were invisible. Ordinary gas had not yet fully collapsed into the dense hot regions required to ignite stars. The cosmos was building silently, and its first structures were hidden from sight. There is something almost tender about that phase. The universe was making homes before it made lamps. Inside and around these halos, ordinary gas began to feel the pull. Hydrogen and helium, the main ingredients left from the Big Bang, slowly drifted inward. The gas was still thin, still cold by stellar standards, but now it had somewhere to go. It was no longer just drifting through a largely featureless universe. It was falling into dark matter wells, guided by gravity into places where density could slowly rise. This is one of the great quiet partnerships in nature. Dark matter seems to have built the gravitational container, and ordinary matter began filling it. The invisible shaped the visible long before the visible could speak for itself. If you could somehow map the early universe in a way that revealed only gravity, you would have seen a growing patchwork of these halos and filaments, a faint architecture spanning space. But if you had looked with ordinary eyes, even impossibly sensitive ones, there would still have been almost no light. The first true structures were real and important, yet still hidden behind darkness. That is part of what makes the early universe feel so different from our own. Today, we trust light. We learn from what shines. We recognize things by color and brightness and form. But the young cosmos was organized first by what did not shine at all. Its earliest history was not written in light. It was written in pull. One of the elegant results of modern computer simulations is that when scientists model a universe filled with dark matter and let gravity do its work over immense spans of time, they see this hidden structure emerge. At first there are small irregularities, then clumps, then halos, then a larger web-like pattern with dense knots and long filaments stretching between them. When ordinary matter is included, it falls into that framework and eventually forms the glowing structures we can actually observe. In other words, the visible universe we know seems to grow naturally inside an invisible dark matter network. This is why galaxies are not scattered randomly through space. They tend to appear where the underlying gravitational framework allowed matter to gather. The bright universe is not floating freely. It is sitting inside older, darker bones. And those bones were already forming during the long quiet ages before the first stars. It also helps explain something subtle but important. When we ask about the oldest structure in the universe, we are not really asking for the oldest thing you could have seen with your eyes. We are asking about the earliest organized pattern that began shaping the future. In that sense, dark matter halos deserve enormous attention. They were among the first places where the universe stopped being merely uneven and started becoming structured. The distinction matters. A tiny density fluctuation is a beginning, yes. But a halo is more than a fluctuation. It is a gathered form, an actual gravitational entity, however invisible. It is one of the first ways the cosmos began turning slight preference into durable architecture. And once that started, more changes became possible. As gas fell into halos, it did not simply settle instantly. It had to cool. It had to compress. It had to lose enough energy for gravity to pull it deeper inward. This process could be slow and delicate, especially in the smallest halos. The early universe did not yet have many of the heavy elements that help gas cool efficiently today. There was mostly hydrogen and helium, simple ingredients in a very simple cosmos. So even here, even with the scaffolding in place, nature moved carefully. Dark matter could gather first because it was freed from many of the complications that affected ordinary matter. But for the visible universe to awaken, gas had to respond in its own slower way. That delay matters because it reminds us that cosmic history is not just about having the right ingredients. It is also about sequence. First the unevenness, then the halos, then the slow infall of gas, then, eventually, conditions dense and hot enough for the first stars. The universe was not improvising wildly. It was unfolding step by step, and every step depended on the one before it. Sometimes, when people hear the phrase dark matter halo, they imagine a crisp boundary, as if a galaxy sits inside a neat invisible shell. In reality, halos are more diffuse and complex than that. Their density is greatest near the center and falls off with distance. They overlap, merge, stretch, and influence each other. They are less like polished containers and more like mounds and valleys in a shared gravitational terrain. Still, the basic idea remains. These were the first great gathering places. And they were big. Even the earliest halos, though tiny compared with later galaxy clusters, were enormous by everyday standards. Some of the first star-forming halos may have contained enough mass to equal hundreds of thousands or millions of suns. Later halos would become far grander. But even at the beginning, the universe was already thinking in scales far beyond anything human instinct can comfortably hold. Yet the mood of the era was not grand in the emotional sense. It was hushed. Vastness can be loud in our imagination, but the early universe was vast and quiet. No bright constellations. No visible drama. Just gravity gathering in darkness, one hidden structure at a time. If you are listening to this late at night, there is something gently fitting about that image. The universe itself had a long night before its first dawn. A dark age filled not with emptiness, but with unseen preparation. Even in silence, it was becoming something. That may be one of the calmest truths in cosmology. The absence of visible light did not mean nothing was happening. Darkness was not inactivity. It was incubation. And in that incubation, another important pattern was taking shape. The halos did not form in total isolation. As time went on, they became connected by a larger scale structure, the beginnings of what would later become the cosmic web. Denser regions gave rise to more halos. Halos merged along filaments. Matter flowed into deeper wells. The universe was beginning to sort itself into a network, though that network was still mostly hidden from any kind of luminous view. This hidden web would one day host galaxies by the billions. But for now, it was an invisible geography. You can think of it as the first draft of the universe we know, a draft made in dark ink. It is also here that the phrase oldest structure starts to take on a deeper meaning. If by structure we mean the earliest enduring arrangement of matter that could influence future growth, then dark matter halos were among the oldest real structures the universe ever formed. They were not the very first fluctuations, but they were the first invisible architecture strong enough to hold the future. Without them, the first stars may have taken far longer to appear, if they could have appeared in the same way at all. Without them, gas would have had no preferred wells to fall into, no hidden centers around which luminous matter could gather. The universe would have remained smoother, dimmer, and far less interesting for far longer. So much of what we love about the night sky may depend on something we have never directly seen. That alone is worth pausing over. Every visible galaxy may be, in a sense, just the glowing announcement of an older invisible structure beneath it. Every spiral arm, every halo of stars, every bright galactic core is like a lantern hung inside a dark matter house that was built first. And because this is a slow journey rather than a rushed one, it is worth letting that picture settle. Before light, structure. Before beauty, groundwork. Before the first visible sign of cosmic complexity, the universe had already spent ages shaping hidden wells in the dark. This was the quiet labor that came before the show. If these calm explorations help you settle in for the night, you can gently support the channel with a like or subscribe, and if you feel like sharing, you can leave a comment about where you're listening from. There is something lovely about many different people, in many different places, drifting together through these old cosmic questions. For now, though, the universe is still mostly dark. The halos are there. The gas is gathering. Gravity has built the first invisible homes. But the rooms are not lit yet. That next step will change everything. Because eventually, in the densest hearts of some of these hidden halos, the gas will fall inward far enough, heat up enough, and compress enough for a new kind of fire to begin. The first stars are still ahead of us. And when they arrive, the universe will no longer be only a structure of darkness and pull. It will begin to glow. Part 4, when the universe finally began to shine. For a very long time, the universe was busy without looking busy. Dark matter had gathered into invisible halos. Ordinary gas had begun its slow descent into those hidden wells. Gravity was at work everywhere, though nothing yet glittered enough to announce it. If you could have crossed that ancient cosmos, it would still have felt more like a waiting room than a finished world. The framework was there. The first homes had been prepared, but the lamps had not yet been lit. And then, after all that darkness, something changed. Not everywhere at once. Not in a sudden flash across the entire universe. But in scattered places, in the deepest pockets of those invisible halos, the gas fell inward far enough, and pressed together long enough, that a new threshold was crossed. The first stars were born. That moment is difficult to overstate. It was not only the beginning of starlight. It was the end of a kind of cosmic innocence. Before the first stars, the universe was simple. Its matter was mostly hydrogen and helium, the plain original ingredients left over from the Big Bang. Its structure was mostly hidden. Its darkness was deep and almost complete. But once stars appeared, the universe gained a new kind of complexity. It gained furnaces. It gained chemistry. It gained light with direction and source and consequence. In a calm way, this was the first real dawn. The first stars are often called population 3 stars, which sounds a little backward. You might expect the earliest stars to be called population I, but astronomers named the different generations in reverse order, based on when they were understood rather than when they existed. So population 3 refers to the first stars of all, the most ancient, the most primitive in composition, and in some ways the strangest. They were born in a universe that still knew almost nothing. There were no rocky planets, no carbon-rich clouds, no oxygen in the ordinary sense we rely on today, no iron in the cores of worlds, no silicon, no calcium, no gold, no phosphorus. Almost all of the familiar elements that make life, stone, oceans, and bodies possible had not yet been forged. The cosmos had only its original stock, mostly hydrogen, a good deal of helium, and tiny traces of lithium. That was it. The universe had not yet learned how to build the periodic table we now take for granted. So the first stars were made from the simplest possible recipe. That matters because it changed the way they formed. Modern stars, including our Sun, are born inside clouds that contain many heavier elements, what astronomers, a little confusingly, call metals. In astronomy, anything heavier than helium counts as a metal. These heavier elements help gas cool. They allow collapsing clouds to shed energy more efficiently, which makes it easier for the gas to fragment into smaller pieces. That is one reason the modern universe can form stars of many different sizes, from modest red dwarfs to giants far larger than the Sun. But the first star-forming gas had no such advantage. It was far more limited in how it could cool. So instead of breaking apart into many smaller dense knots, the gas in those early halos may often have remained in larger collapsing clumps. And that likely meant the first stars were often much more massive than many stars we see today. Not every model gives the exact same picture, and astronomy is still refining this story, but the broad idea is clear enough. The first stars were probably different from our Sun in a very deep way. They were hotter, larger, briefer, more intense. They lived like giant blue-white fires in a universe that had never seen light born this way before. Imagine the first one. For tens or perhaps hundreds of millions of years after the Big Bang, the universe had known only diffuse afterglow, the fading microwave memory of its hot beginning. But that ancient light was everywhere and nowhere, stretched thin across space. A star was something new. A star was local, concentrated. A single place where gravity had gathered matter so densely that the center became hot enough for nuclear fusion to begin. That process is one of the great miracles of physics, though it is so natural that it hardly needs the word miracle. A star forms when gravity keeps squeezing gas inward. As the gas collapses, its center grows denser and hotter. Eventually, if enough mass is present, the core temperature climbs to extraordinary levels, millions of degrees. At that point, hydrogen nuclei no longer simply drift near one another. They collide with enough force to fuse. In that fusion, a tiny bit of mass is converted into energy, and the star begins to shine. Gravity pushes inward. Fusion pushes outward. A balance is born. And just like that, the darkness gains a fire. The first stars may have begun appearing when the universe was perhaps around 100 to 200 million years old, though the exact timing is still studied. In human terms, that sounds ancient beyond imagination. But in cosmic terms, it was early enough to count as the first faint pulse after a very long-held breath. There is something almost intimate about that timescale. We often think of the universe in terms so large that every event feels hopelessly distant. But here the story becomes easier to feel. The cosmos spends a while in darkness, slowly gathering. Then, after enough patience, the first points of light arrive. It is not unlike dawn in the most basic sense. First the long blackness. Then, in a few places, brightness. But the first stars were not gentle dawn stars like the ones that now appear in a calm evening sky. They may have been monsters by comparison. Because the gas could not cool and fragment as efficiently, many of these early stars may have reached tens or even hundreds of times the mass of the Sun. A star that massive does not live quietly. The more massive the star, the hotter its core, and the faster it burns through its fuel. So these first stars, though enormous, were probably short-lived. Some may have shone for only a few million years, perhaps even less in certain cases. That sounds long to us, but compared with the Sun's expected lifetime of roughly 10 billion years, it is astonishingly brief. The first stars lived fast. They poured out tremendous radiation into the surrounding darkness. Their ultraviolet light began altering the universe around them, stripping electrons from nearby hydrogen atoms and gradually changing the state of the intergalactic medium. This long process, carried out by many generations of early stars and galaxies, is known as reionization. The name sounds technical, but the core idea is simple. After the universe had once become neutral, with electrons and protons settling together into atoms, these new stars began flooding parts of space with enough energetic light to tear those atoms apart again. So the first stars did more than shine. They transformed their environment. Their light traveled outward through a cosmos that had waited a very long time for visible illumination. Around each young star, and around the earliest groups of stars, there would have been growing bubbles of ionized gas, regions where the darkness was not only broken by light, but physically changed by it. Over time, more bubbles formed. They expanded. They overlapped. The universe did not become transparent to ultraviolet light everywhere all at once, but patch by patch, through the accumulated labor of its first luminous generation. It is one of the quietest grand renovations in cosmic history. And yet, for all their brilliance, the first stars were still fragile in a deeper sense. They were trying to form in a universe that had never done this before. The gas conditions were unusual. The cooling channels were limited. The balance between collapse, heating, and radiation was delicate. Some halos may have formed only one massive star, or just a handful, before their own radiation heated the surrounding gas and made further star formation more difficult for a while. The first dawn did not unfold in comfort. It unfolded in tension. That tension gives these stars a special place in the story. They were pioneers in the truest sense. They were the first objects to gather matter so densely that fusion could begin, and in doing so, they changed the rules for everything after them. Because the first stars were not only sources of light, they were the first great forges. Inside a star, simple elements can be turned into heavier ones. Hydrogen fuses into helium. In more massive stars, helium can be fused into carbon and oxygen, and then into still heavier elements in later burning stages. The most massive stars run through this sequence quickly, building layer upon layer in their interiors, like an onion made of nuclear fire. But there is a limit. Fusion beyond iron no longer releases energy in the same useful way. Once a very massive star builds an iron core, its balance becomes unstable. Gravity, which had long been held off by the outward pressure of fusion, finds its chance again. And then the star dies. Some of the first stars may have collapsed directly into black holes. Others may have ended in tremendous explosions, supernovae of extraordinary power. In the most massive cases, some may even have died in pair instability supernovae, a particularly dramatic kind of explosion that can completely unmake the star, leaving no remnant behind. In such an event, the entire star can be blown apart, throwing newly forged elements into space. This is the beginning of enrichment. Before the first stars, the universe had almost no heavy elements. After the first stars lived and died, the cosmos was no longer chemically innocent. Carbon was now possible. Oxygen was now possible. Silicon, magnesium, iron, The raw ingredients for future rocky planets, for mineral worlds, for complex chemistry, began as ash from stellar death. This is one of the most beautiful reversals in the story. The first stars were not simply bright objects decorating the darkness. They were factories, and then they were explosions, and through those explosions they made the universe more capable of complexity than it had been before. The first stars taught the cosmos how to make new matter. Everything heavier than helium in your body, every atom of calcium in bone, every iron atom that lets blood carry oxygen, every oxygen atom you have ever breathed, belongs to a story that begins here. Not with our sun, not with Earth, but with older stars, and before those, with the first generation that began the work. You are, in a very literal sense, downstream from the first stellar fires. That fact is often said quickly, as if it were merely poetic. But it is more than poetic. It is a direct statement about physical ancestry. The early universe was too simple to build planets like ours or living chemistry like ours. Those things required generations of stars to take hydrogen and helium and slowly convert them into a richer universe. The first stars were the opening line in that long chemical sentence. Still, because this is a sleep story and not a race, it helps to imagine their lives more gently. Picture one of those invisible dark matter halos we spoke about before. Within it, gas has been falling inward for a long time. The center grows denser. Molecules of hydrogen, in their limited early universe way, help the gas cool just enough for the collapse to continue. The central region tightens. Temperature rises. Pressure builds. Then, at last, ignition. A star appears where before there had only been darkness and falling gas. Around it, the young universe remains immense and silent. But now there is a source, a direction, a place you could point to and say, there. That is where the first true starlight is coming from. Then its light begins to alter the gas around it. Then its winds, or radiation, push back on the infalling material. Then it races through its fuel. And then, before cosmic history has barely begun in earnest, it dies, scattering new elements or collapsing into an early black hole that may itself help seed future structure. Even in death, it leaves the universe change. This is why the first stars matter so much even though we have never directly observed one. They set off a chain reaction of consequence. They changed the chemical makeup of space. They helped drive reionization. They prepared the conditions for later, smaller, more complex generations of stars. They marked the moment when the universe shifted from hidden structure to visible radiance. Without them, there would have been no later galaxies in the form we know, no rich interstellar clouds, no planets made of stone and metal, no deep cosmic chemistry. The first stars did not merely shine. They opened the future. There is another quiet detail here that is easy to miss. The first stars were probably not the beginning of beauty in the human visual sense. They may have been so hot and short-lived and isolated that the scene, if we could somehow watch it, would not resemble the soft richness of the modern night sky. There were no mature galaxies yet with sweeping spiral arms. No familiar constellations. No settled star fields. The beauty of the moment lies more in what it means than in what it might have looked like from a comfortable distance. It was the beauty of firstness. The first star means the first local defeat of darkness, the first true furnace, the first heavy elements, the first step toward a universe that could eventually contain complexity, fragility, and life. And yet the darkness did not vanish. Not immediately. The first stars appeared in islands, not in a continuous glowing sea. Between them lay enormous gulfs of dark space. The universe was still mostly empty to the eye. The Dark Ages did not end with a single switch being flipped. They ended unevenly, region by region, as more stars formed, more light accumulated, and more of the intergalactic medium was transformed. That gradualness matters because it keeps the story humanly believable. Nature rarely hurries in the way we expect. Even its revolutions often unfold as countless local events that slowly add up to a cosmic change. So the first stars did not instantly give us the universe we know, but they made it possible. Over time, enriched by the ashes of these early giants, later star-forming clouds could cool more efficiently and break into smaller pieces. New generations of stars formed with heavier elements mixed in. Some were more moderate in size. Some lived longer. Some gathered in larger numbers. The earliest galaxies began taking shape as these processes repeated and combined. In that sense, the first stars were not the completed dawn. They were the first hints of morning. And like any first light, they changed how the rest of the landscape could emerge. If these slow journeys through the universe help you unwind, you can gently support the channel with a like or a quiet subscribe. And if you feel like it, leave a comment about where you're listening from tonight. It's always calming to imagine all these distant listeners gathered beneath the same old cosmic story. But in the universe itself, the story is still just beginning. The first stars have burned. Some have already died. Their light has disturbed the darkness, and their deaths have salted space with the first heavy elements. The cosmos is no longer made only of simple gas and invisible scaffolding. It is becoming richer now, more structured, more capable of building enduring things. And from these first isolated fires, larger communities of light will slowly emerge. The universe is about to learn how to gather stars together. It is about to make its first galaxies. Part 5: The First Galaxies and the Slow Gathering of Light. A single star can change the darkness around it, but a galaxy changes the darkness in a different way. It does not simply interrupt the night, it begins to organize it. After the first stars were born, the universe was no longer completely asleep. Here and there, inside the invisible dark matter halos that had formed in the long cosmic dark ages, small fires had already appeared. Some of those stars burned fiercely and briefly. Some died in explosions that scattered the first heavy elements into space. Some may have collapsed into black holes. The universe had crossed an important line. It had gone from hidden structure to visible light. But one star, even a giant ancient one, is still only a beginning. What came next was slower, richer, and in some ways even more beautiful. The first isolated lights began to gather into communities. Small systems of stars, gas, dark matter, and turbulence slowly emerged from the darkness. These were the first galaxies, and with them, the universe began to look less like a scattered collection of sparks and more like a place with real architecture. If the first stars were like the first campfires in a long night, the first galaxies were like the first villages of light. That does not mean they looked anything like the majestic galaxies we know today. There were no fully mature spirals yet, no elegant, broad pinwheels like the Milky Way drifting through the dark with calm confidence. The earliest galaxies were smaller, rougher, more chaotic. They were young in every sense. But they were also the beginning of something the universe had never had before: stable, repeated places where stars could keep forming, gas could keep gathering, and structure could keep deepening. This was the moment when the cosmos began to build lasting homes for light. To understand how that happened, it helps to remember where we are in the story. The first stars had formed inside dark matter halos, those invisible wells in the cosmic landscape. Ordinary gas had fallen into those wells, compressed, heated, and in some cases ignited into stars. But once those first stars appeared, they did not leave their surroundings unchanged. Their radiation pushed on nearby gas. Their heat altered the environment. Their deaths enriched space with heavier elements. In a quiet but profound way, they made the universe less simple than it had been before. And that mattered. Because once heavy elements entered the picture, gas gained new ways to cool. And cooling is one of the most important, and least dramatic, powers in the universe. A gas cloud that cools more effectively can collapse more efficiently. A collapsing cloud can fragment more easily. and a cloud that fragments can form many stars rather than only one or two giant ones. In that sense, the first stars helped make later star formation more fertile. The earliest galaxies may have formed when multiple pockets of gas within a halo began producing stars over time, instead of just a single massive burst. More halos merged. More gas flowed inward. More stars appeared. Little by little, a simple gravitational well began turning into something more recognizable, a proto-galaxy, a young galaxy in the making. That word, proto-galaxy, is useful because it reminds us not to imagine finished forms too soon. The first galaxies were not completed works. They were rough drafts. They were systems still assembling themselves, still being reshaped by inflows of gas, stellar winds, radiation, explosions, and the restless pull of gravity. If a modern mature galaxy is like a city with neighborhoods, roads, and a settled rhythm, the first galaxies were more like fast-growing frontier towns. Important, yes. Stable enough to matter, yes. But not polished. Still, they were real galaxies in the deepest sense. They were places where many stars could exist together inside a common gravitational environment, shaped by dark matter, fed by gas, and connected to the larger cosmic web that was beginning to emerge across the universe. And they were small. Compared with the Milky Way, many of the earliest galaxies were tiny. Some may have contained only a few million stars, or even fewer, while the Milky Way likely contains on the order of hundreds of billions. That difference is hard to emotionally grasp. It means that some of the first galaxies were not just smaller than our own. They were smaller by a factor so large it almost sounds unfair. But that is how the universe often works. It begins with modest versions of things, then lets time and merging build the grander forms later. A small galaxy is still an astonishing thing. Imagine it drifting in the deep early cosmos, a dark matter halo holding together a cloud of gas, with a growing population of stars flickering inside it. The gas is not calm. Some regions are collapsing. Some are being blasted outward by stellar radiation or supernova explosions. New stars are forming while old ones are already dying. Heavy elements are beginning to mix into the surrounding material. Black holes may be forming in some regions. Nothing about it is static, but it is no longer just a loose collapse. It is becoming an enduring system. In those first galaxies, the universe learned a new habit. It learned how to keep making stars. That is one of the key differences between the first isolated stellar events and the first galaxies. A lone early star, or a very small first-generation system, is a beginning. A galaxy is a machine for repetition. It can hold gas, gather more gas, form stars, lose some gas, pull in more, and continue the cycle. It becomes an engine of cosmic development. Once galaxies exist, the universe has entered a more productive phase of its life. This is where the story starts to feel less like ignition and more like growth. And growth, in the universe, is rarely smooth. The earliest galaxies did not develop in isolation for very long. The dark matter halos that hosted them were themselves moving through an expanding cosmos, drawn together along larger gravitational patterns. Small halos merged into larger ones. Gas streamed along filaments. Young galaxies encountered one another. Some passed nearby and disturbed each other. Some collided and combined. Some were swallowed by larger systems that were just beginning to become possible. This merging process is one of the great shaping forces in cosmic history. When two young galaxies interact, gravity begins rearranging everything. Gas clouds can be compressed, triggering new waves of star formation. Stellar orbits can be disturbed. Dark matter halos can combine. What was once two small systems can slowly become one larger, messier, more massive structure. This did not always happen quickly. Sometimes the process took hundreds of millions of years. Sometimes a smaller galaxy was stripped apart gradually, its stars and gas absorbed into the larger one. Sometimes repeated mergers built up larger galaxies piece by piece, like a shoreline slowly built from many incoming tides. This is one of the reasons the universe we see today contains so much complexity. Galaxies were not simply born finished. They were assembled through long histories of gathering and collision, and that process began surprisingly early. The first galaxies were not meant to stay small forever. They were the starting pieces in a much longer game of cosmic construction. Over time, as they merged and accreted more gas, some grew into larger and more complex systems. New generations of stars formed from material already enriched by earlier stars. This meant each round of star formation could produce a different universe than the round before. More heavy elements, better cooling, more diversity in stellar types, more dust, more chemistry, more possibility. In this way, galaxies are not just collections of stars. They are memory systems. A galaxy keeps the record of its own past inside itself. Its older stars remember earlier chemical conditions. Its younger stars reveal later enrichment. Its shape can carry the imprint of past mergers. Its halo reflects older gravitational history. A galaxy is like a long, slow autobiography written in light and motion. The first galaxies, then, were the first places where the universe began storing a deeper history of its own development. There is something very calm about that idea. The cosmos was no longer only making events. It was beginning to make places where events could accumulate. That is why galaxies matter so much in the broader story of the oldest structure in the universe. They are not the oldest structure themselves, of course. The oldest pattern lies further back, in the first fluctuations and the early hidden scaffolding of dark matter. But galaxies are where that invisible blueprint becomes legible in a more familiar way. They are where the ancient irregularities, stretched out from the earliest moments of time, become visible as real long-lived systems of light. In other words, galaxies are part of the universe's translation process. The early ripples became halos. The halos gathered gas. The gas formed stars. The stars enriched the gas. The systems merged and matured. And slowly, the invisible mathematics of the early universe became visible beauty. That transformation took time, and it did not happen evenly across all regions. Some parts of the universe were denser and more favorable for early galaxy formation. Some were emptier and slower to develop. Even now, the cosmos is not uniform. It is web-like, clustered, laced with filaments and voids. That unevenness was already shaping the fate of the first galaxies. They tended to emerge where the underlying structure gave matter a stronger reason to gather. This is another way of saying that the first galaxies were not random lights scattered in an indifferent darkness. They were guided by the hidden geography of the cosmos. And the geography itself had ancient roots. When we look far out into space with powerful telescopes, we are also looking back in time. Some of the faintest, earliest galaxies ever observed appear to us as they were in the first few 100 million years after the Big Bang. We do not see them in perfect detail. They are often tiny, dim, and difficult to study. But even these faint glimpses tell us something important. The young universe, though still early, was already capable of building surprisingly organized systems of stars. That is one of the steady lessons of astronomy. The universe does not waste time once the conditions are right. It can remain patient for ages, and then, once a threshold is crossed, it can begin building complexity with quiet determination. The first galaxies may also have played a major role in finishing what the first stars began, the reionization of the universe. Those early stars, especially when gathered into galaxies, produced large amounts of energetic light. Over time, the combined radiation from many early galaxies helped transform the intergalactic medium, ionizing more and more hydrogen across vast regions of space. In that sense, galaxies did not merely shine within the universe. They helped reshape the state of the universe itself. Small systems, huge consequences. And because this is a sleep story, it is worth pausing to notice how soft that process sounds when stripped of its technical language. Countless small galaxies, far back in time, each forming stars inside dark matter halos, each sending light out into the surrounding darkness, each helping to make the universe more transparent and more structured than it had been before. No sudden switch. No single ruler commanding the transition. Just accumulation. Many small lights, gradually changing everything. Nature often works that way. Enough small things, repeated patiently, become a new reality. The first galaxies were also the beginning of a more social universe. Before them, stars were mostly solitary events in a cosmic sense, isolated fires inside dark halos. But galaxies brought stars into common environments. This matters because once stars share a system, their histories intertwine. One generation can enrich the gas from which the next is born. Explosions from one region can influence collapse in another. A central black hole, if one forms and grows, can begin affecting the larger system. Motion becomes collective. Gravity becomes layered. A galaxy is not just a container. It is an ecosystem. That ecosystem was still primitive in the beginning, but it would only grow more complex with time. Over hundreds of millions and then billions of years, the descendants of these first galaxies would continue to merge, stretch, distort, and mature. Some would become the ancestors of large spiral galaxies. Some would help form giant elliptical galaxies. Some would remain small and faint, relics of ancient conditions. Some would be torn apart and absorbed into larger structures, leaving their stars behind as quiet evidence of past mergers. Even our own Milky Way carries signs of this kind of history. It likely grew in part by swallowing smaller galaxies over time. The modern universe is full of these layered stories. But all of it begins here, with the first galaxies learning how to gather stars and hold them together. In a way, galaxies are where the universe first begins to seem inhabited, even though life is still unimaginably far away. Not inhabited by organisms, of course, but by patterns, by recurring structure, by places with ongoing internal history. Before galaxies, the cosmos is mostly setup and ignition. With galaxies, it becomes a world of neighborhoods. And neighborhoods can become cities. That is where the story naturally goes next. Because once galaxies exist, and once many of them begin forming in the same larger regions of space, gravity does not stop at the scale of a single galactic home. The same patient force that gathered matter into halos and stars and galaxies begins working at an even larger level. Galaxies themselves start becoming part of bigger systems. They are drawn into groups, then clusters, then larger and larger patterns that stretch across the cosmic web. But before we leave this moment, it is worth lingering with one final image. Picture the early universe no longer as a dark plain with only occasional fires, but as a place where the first true islands of light are beginning to appear. They are small, uneven, turbulent, and far apart. Yet they are real. They are gathering gas, making stars, and preserving the memory of ancient structure. They are the first galaxies, and with them the universe begins to look less like a beginning and more like a place. If these slow journeys through the cosmos help you settle into sleep, you can gently support the channel with a quiet like or subscribe. And if you feel like it, leave a comment about where you're listening from tonight. It always feels fitting that so many distant points of awareness can gather around the story of how the first distant lights once gathered too. For now, though, the galaxies are still young. The universe is still learning scale. Its early islands of light are beginning to find one another, and gravity is preparing a bigger arrangement. The cosmos is about to discover what happens when galaxies themselves begin to live together. Part 6: When Galaxies Began Living Together. A galaxy can feel enormous when you think about it on its own. Even a modest galaxy contains stars beyond counting, clouds of gas drifting across impossible distances, dark matter wrapping around it like an invisible domain, and enough time inside it to make human history feel thinner than a strand of smoke. A single galaxy is already so large, so old, and so full of motion that it can seem like the natural endpoint of cosmic structure. As if once the universe learned how to build galaxies, it had already built something close to complete. But gravity is rarely satisfied with one layer of order. Once the first galaxies appeared and began to multiply across the young universe, they did not remain alone. They were not born into sealed boxes, each drifting forever in perfect isolation. They were part of a much larger landscape, shaped by the same ancient blueprint that had guided matter from its first tiny irregularities. And in the denser parts of that landscape, galaxies began to notice one another. They began to gather. They began to share the same larger gravitational neighborhoods. This was the next quiet turning point in cosmic history. The universe had learned how to make stars. Then it learned how to collect stars into galaxies. And now it was beginning to do something larger still. It was learning how to collect galaxies together. If the first galaxies were like the first villages of light, then what came next was the beginning of cities. Not cities in the human sense, of course. No streets. No architecture built by minds. No voices. But there was something city-like in the new arrangement. Galaxies that had once been separate now started occupying common space. Their motions became linked. Their futures became shared. They were no longer just individual islands of light in a dark ocean. They were becoming members of larger systems. These systems came in stages. Some galaxies gathered into small groups. Others fell into larger and richer collections called clusters. A group might contain a few galaxies, or a few dozen, loosely bound together by gravity. A cluster could contain hundreds or even thousands. And between those bright galaxies, there was much more than empty space. There was dark matter, as always, forming most of the mass. There was also hot gas, stretched across the cluster in vast clouds so heated that it shone not in visible light, but in X-rays. A galaxy cluster, then, was not simply a pile of galaxies. It was a whole environment, a shared gravitational world. This is one of the strangest shifts in perspective astronomy asks of us. Just when you become comfortable thinking of a galaxy as an immense thing, the universe calmly places it inside something larger. Our own Milky Way is not alone. It belongs to a small collection called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf galaxies orbiting within the same broader gravitational family. That group is modest by cosmic standards, but it gives us a useful feeling for the idea. Galaxies can have neighbors. They can orbit common centers. They can approach one another slowly over billions of years. They can merge. They can be pulled, distorted, and changed by the presence of others. Now imagine that on a larger scale. Imagine hundreds of galaxies gathered into one common structure, each moving through the cluster's gravity, each carrying its own stars, gas, black holes, and long internal history, while also participating in a wider story. Some are spirals. Some are ellipticals. Some are old and quiet. Some are still forming stars. Some are being stripped of gas as they move through the hot cluster medium. Some are colliding. Some are being slowly swallowed by larger neighbors. A cluster is not still. It is a place of deep, patient activity. And like every earlier step in cosmic history, it began gradually. The earliest galaxies formed in denser parts of the universe, where dark matter halos and gas had more reason to gather. Those denser regions did not stop exerting influence once galaxies appeared. On the contrary, they became even more important. The same web-like pattern in dark matter that guided galaxy formation also guided galaxy clustering. Matter was not distributed at random. It flowed along invisible structures, gathered into nodes, and over time those nodes became crowded places in the universe. A group or cluster is what happens when gravity keeps saying yes to gathering. At first, small halos merged into larger halos. Small galaxies formed in them. Then those galaxies, and the dark matter halos containing them, drifted toward larger concentrations. More material kept falling in. More galaxies arrived. Some systems remained small groups. Others kept growing until they became clusters of astonishing mass. A mature galaxy cluster can weigh as much as 1,000 trillion suns, or even more. Most of that mass is not in the visible galaxies. Most of it is dark matter. Some of it is in the form of hot, thin gas spread between the galaxies. And only a smaller fraction is the starlight we can easily imagine. That alone tells you something important about the universe. Even at the scale of great clusters, the visible part is not the whole story. What shines is only part of what matters. In a strange way, galaxy clusters are honest places. They reveal how little of the universe is visible. If you could somehow drift through a cluster with ordinary eyes, you would see galaxies scattered across an immense volume of space. Some would be larger and brighter than others. Toward the center, you might see a giant elliptical galaxy, enormous and ancient, swollen by mergers and sitting close to the deepest part of the cluster's gravitational well. Around it, smaller galaxies would move in long arcs and patient orbits. But what you would not see would be just as important. You would not see the dominant dark matter halo holding the cluster together. You would not see the great atmosphere of hot gas that fills the space between galaxies. You would only sense that this whole enormous region is one connected thing because gravity has made it so. That hidden gas is worth pausing over, because it surprises many people the first time they hear about it. The space between galaxies in a cluster is not simply empty. It contains thin plasma heated to tens of millions of degrees. That sounds almost impossible, and in everyday terms it is. The gas is extremely hot, but also extremely diffuse, so it would not feel like the kind of heat we know from a flame or a stove. Yet across the great volume of a cluster, there can be more mass in this gas than in all the stars inside the galaxies combined. So even between galaxies, a cluster is full of presence. This hot gas matters because it tells us how active the cluster has been. As galaxies and matter fall inward, as smaller groups merge into larger ones, gravitational energy is converted into heat. The cluster becomes not just a gathering of galaxies, but a deep reservoir of energy and motion. We can observe that gas in X-rays, and it reveals structures, shock fronts, and disturbances that hint at older collisions and continuing growth. A cluster, then, is not just a collection. It is a memory of assembly. That phrase works at almost every level of cosmic structure. A galaxy remembers its mergers. A cluster remembers the infall of groups and galaxies. The universe keeps its history not in written records, but in motion, chemistry, temperature, and shape. And clusters can be dramatic places, though their drama unfolds on timescales so long that it remains calm to the imagination. Galaxies inside clusters do not move gently in the everyday sense. They can race through the cluster environment at speeds of hundreds or even thousands of kilometers per second. Yet because the distances are so immense, encounters still take vast spans of time. A galaxy passing through the dense central regions of a cluster may have its gas stripped away by the pressure of the hot intracluster medium, almost like air resistance on an unimaginably larger and thinner scale. As it moves, its star-forming material can be peeled off, leaving long tails of gas behind it. In this way, the cluster slowly changes the kinds of galaxies it contains. Spirals can lose their gas and become quieter. Star formation can fade. Over time, a dense cluster can become home to many older, redder galaxies, systems that have largely finished the most active phase of their stellar lives. This is one reason clusters are so fascinating. They do not merely gather galaxies. They reshape them. A galaxy living alone has one kind of life. A galaxy living in a crowded, gravitationally intense environment has another. That same truth exists on smaller scales too. Even in the local group, the Milky Way and Andromeda are slowly moving toward one another. They are expected to merge billions of years from now, forming a larger galaxy from the union of two already immense systems. That future event will be spectacular in scale, though probably not violent in the way human instincts imagine, since stars are separated by such vast distances that direct stellar collisions are rare. The greater effect will be gravitational. Orbits will be rearranged. Gas clouds will be compressed. New star formation may flare for a time. Structure will change. A new galactic form will emerge. That is what gravity does when galaxies live together. It makes solitude temporary. The first groups and clusters in the universe likely began forming as galaxies accumulated in the densest knots of the cosmic web. Those knots were the descendants of the earliest overdense regions, the places where matter had always had a slight tendency to gather. The story, once again, goes all the way back to the beginning. The same ancient ripples in the early universe that led to dark matter halos and first galaxies also set the stage for groups and clusters. The universe was not inventing a new logic at this point. It was continuing the one it had always followed. Slight unevenness became gathering. Gathering became halos. Halos became galaxies. Galaxies became communities. And those communities became some of the largest gravitationally bound things in the cosmos. That phrase, gravitationally bound, is worth explaining softly. It means that the galaxies in a group or cluster are not merely passing by one another in a temporary coincidence. They are held together by gravity strongly enough that they form a real system. They may move within it. They may merge. They may fall toward the center or orbit through the outskirts. But they belong to the same larger structure. A cluster is, in a sense, a galaxy-scale family held together by a dark matter home so vast that individual galaxies become like moving parts inside it. And there is one more layer of beauty here. Clusters can bend light. Because they contain so much mass, especially dark matter, galaxy clusters warp spacetime strongly enough to act as gravitational lenses. Light from more distant galaxies passing through or near the cluster can be bent, stretched, and magnified. Sometimes we see long arcs of distorted light around a cluster, the warped images of galaxies lying far behind it. In this way, a cluster does not only gather matter. It changes the appearance of the universe beyond it. There is something almost dreamlike about that. One of the largest structures in space can become a lens, quietly curving the light of even more distant worlds. The cluster is not only an object in the universe. It becomes a way of seeing deeper into the universe. This lensing effect also gave astronomers one of the clearest ways to understand that dark matter must be real. The visible galaxies alone do not contain enough mass to explain the lensing we observe. Something unseen is helping hold the system together and curve the light. Once again, the invisible reveals itself through consequence. It is hard not to admire how consistently the universe works this way. Again and again, its deepest structure is carried by things we cannot directly see. And yet, for all their scale, clusters are still not the end of the story. That may be the most humbling part. You can stand in imagination inside a galaxy cluster and feel that you have arrived at something close to the largest possible arrangement. Hundreds or thousands of galaxies, all gathered into a shared gravitational environment, wrapped in dark matter, filled with hot gas, bending light from the distant cosmos. Surely this must be near the top of the cosmic ladder. But the universe still has larger patterns waiting. Clusters themselves are not scattered randomly. They, too, are arranged along bigger structures. They can belong to superclusters, looser associations stretching across hundreds of millions of light years. And beyond even that lies the cosmic web, the great pattern of filaments and voids that links the largest scales we can observe. So part 6 sits in a beautiful middle ground. Here, the universe reveals that galaxies are social. They gather into families, neighborhoods, and crowded cities of light. Gravity extends its reach beyond the individual galaxy and creates larger systems with shared histories. Yet even those vast clusters are still only parts of something greater. Before we move on, though, it is worth staying with the feeling of a cluster for one more quiet moment. Picture a dark expanse where galaxies are no longer lonely. Hundreds of them drift through one common field of gravity. Between them, hot gas glows in wavelengths invisible to our eyes. Around them, dark matter forms the dominant hidden mass. Toward the center, giant galaxies sit like old rulers of a crowded realm. Around the edges, smaller galaxies continue falling inward, still being added to the structure. Everything is in motion. Everything is connected. Everything is old enough to feel patient. A cluster is what happens when the universe begins to think socially. If these slow journeys help you relax and settle into sleep, you can gently support the channel with a quiet like or subscribe. And if you feel like it, leave a comment about where you're listening from tonight. There is something comforting about many people, in many places, listening to the story of how galaxies learned to live together. For now, though, gravity is still not finished. The groups have formed. The clusters have grown. The galaxies have found themselves inside larger homes. But beyond these crowded cities of light, the universe still holds broader arrangements, loose but immense, patterns so large that even clusters begin to look like points on a map. Next, the cosmos will stretch our sense of scale again. Because galaxies can live together. And clusters can, in their own vast way, live together too. Part 7, The Vast Realms Beyond Clusters. A galaxy cluster already feels like it should be enough. Hundreds or even thousands of galaxies, each one carrying stars beyond counting, all held together in one enormous gravitational system. Hot gas filling the space between them. Dark matter outweighing everything we can actually see. Light from more distant galaxies bent and stretched as it passes through. If you pause there for a moment, it already feels like you have reached one of the upper floors of cosmic size. A galaxy is immense. A cluster is vastly larger. What more could there really be? And yet the universe is never finished with scale when we think it might be. Beyond galaxy clusters, there are broader arrangements. Looser. Larger. Less tightly bound in the ordinary gravitational sense. They are not as compact as clusters, and in some ways not as cleanly defined, but they are real patterns in the distribution of matter across the universe. Immense regions where many groups and clusters of galaxies are gathered into larger territories. These are what we call superclusters. The name sounds almost theatrical, but in this case it earns the drama quietly. A supercluster is not a single galaxy enlarged, and not just one cluster stretched wider. It is something more like a region of the cosmos where clusters themselves are gathered in a shared large-scale arrangement. If clusters are cities of galaxies, superclusters are the broad provinces that contain many cities, many roads between them, and vast open land in between. This is where the story of the universe becomes less about isolated objects and more about geography. When people first learn astronomy, they often imagine space as a kind of random scatter. A galaxy here, another there, maybe a cluster somewhere else. But the real universe is more organized than that. Not neat, not symmetrical, not laid out like tiles on a floor, but organized in a deeper way. Matter gathers in patterns. There are dense regions and sparse ones. There are long strands of galaxies and clusters, and there are enormous empty spaces where very little matter resides. Even at the largest scales, the universe has texture. Superclusters are part of that texture. Our own galaxy, the Milky Way, belongs to a small group of galaxies called the local group. That local group is part of a larger cluster-rich region known as the Virgo supercluster. And in more recent decades, astronomers have come to describe an even larger flow-based structure called Laniakea, a vast region containing many galaxy groups and clusters, including our own, all moving in relation to a deeper gravitational basin. Laniakea is a beautiful name. It comes from Hawaiian and is often translated as something like immense heaven or unmeasurable heaven. That feels appropriate, because the scale involved is difficult to hold in the mind for very long. Laniakea stretches across roughly 500 million light-years. That means if light, moving at the fastest speed anything can travel, set out from one side of that structure, it would take about 500 million years to reach the other side. And that is just one supercluster scale region in the observable universe. It is worth slowing down with that for a moment. 500 million years is such a large span that it becomes abstract almost instantly. On Earth, 500 million years ago, complex life in the oceans was only beginning to diversify in ways that would eventually lead to the long later story of animals, plants, and people. Entire worlds can change in a tiny corner of one planet while a single beam of light is still trying to cross one great cosmic structure. That is the kind of scale superclusters live on. But they are not like clusters in every way. This distinction matters. A galaxy cluster is usually gravitationally bound. Its galaxies are held together strongly enough that the system behaves as one definite structure. A supercluster is often looser. The whole thing is not always destined to collapse into one tidy, bound object. Because the universe is expanding, and because dark energy is accelerating that expansion on the largest scales, some of the more distant parts of a supercluster may never truly come together. They are part of the same broad pattern, the same large territory, but not always part of one tightly held future. That makes superclusters feel strangely gentle compared with clusters. They are less like a crowd pressed close together and more like a wide region whose members belong to the same larger terrain. Perhaps the easiest way to imagine it is to think about drainage basins on a continent. Rain falling in one place ends up in one river system. Rain falling elsewhere ends up in another. The exact raindrops may be far apart, but they still belong to the same broader pattern of flow. In a similar way, galaxies and clusters can move through space in ways that reveal larger basins of gravitational influence. That is part of how astronomers describe structures like Laniakea, not simply by drawing circles around visible matter, but by tracing how galaxies flow through the large-scale landscape of gravity. This is one of the more beautiful turns in cosmology. The universe is not just full of objects. It is full of motion with memory. Galaxies drift, clusters gather, and the direction of that motion helps reveal the hidden shape of larger structures. If clusters are where galaxies began living together, then superclusters are where whole communities of clusters begin sharing the same broader cosmic terrain. And like everything else in this story, superclusters did not appear out of nowhere. Their roots go back to the same ancient blueprint we have been following from the beginning. The first tiny irregularities in the early universe were not simply seeds for individual galaxies. They were the starting hints of structure on many scales at once. Small fluctuations grew into halos, halos into galaxies, galaxies into groups and clusters. And in the denser, larger-scale regions, the same ancient preferences continued shaping matter into supercluster-sized patterns. This is one of the calmest truths in cosmology. The universe keeps building with the same basic rule. Slight unevenness, given gravity and time, becomes structure. And time, in this case, means billions of years. Over immense spans, clusters of galaxies formed in the densest nodes of the cosmic web. Between them lay filaments, long bridges of matter along which galaxies and groups could drift inward. Larger-scale regions became recognizable not as isolated clumps, but as connected domains. Superclusters are what those domains look like when the universe has had enough time to let the pattern deepen, but not enough to overcome cosmic expansion entirely on the grandest scales. That may sound subtle, but it is part of why superclusters feel so different from the structures we normally imagine. They are not like mountains or planets or even galaxies, with crisp edges and obvious forms. Their boundaries can be fuzzy. Their internal dynamics can be complex. Their identity comes partly from where matter is concentrated, and partly from how it moves. A supercluster is not an object in the way a star is an object. It is more like a region of cosmic weather made durable over unimaginable time. That softness is part of their beauty. When astronomers map the universe on very large scales, they do not see isolated superclusters scattered like marbles in a box. They see a much richer pattern. Superclusters are connected by filaments and separated by voids. Dense regions taper into thinner strands. Some domains appear like giant walls or elongated chains. Others spread out more irregularly. The largest structures do not really resemble neat spheres or clean disks. They resemble networks. And networks have a different emotional texture than objects. They feel alive in a quiet way. They suggest relationships rather than isolation. This is where the universe starts feeling less like a museum of separate things and more like an ecosystem of connections. The Virgo supercluster, the long familiar large structure containing the Virgo cluster and many surrounding groups, gave astronomers an early way to place the Milky Way inside a larger context. For a long time, it was a useful answer to the question of where we live in the cosmic hierarchy. Earth is in the solar system. The solar system is in the Milky Way. The Milky Way is in the local group. The local group is within the Virgo supercluster. Already that was enough to make the mind go quiet. Then came more refined mapping, more velocity data, more careful efforts to understand how galaxies actually move through the local universe. That led to the identification of Laniakea as a still larger flow-defined region, one in which the Virgo supercluster could be understood as a part rather than the final answer. This is one of the humbling habits of astronomy. Each time we think we have named the largest neighborhood that matters, better maps reveal that the neighborhood belongs to something bigger. It is tempting to imagine this process going on forever, scale beyond scale, but the universe does seem to have limits in how far structure meaningfully grows. On the very largest scales, if you average enough volume, the universe becomes close to homogeneous again. No matter how grand the walls, filaments, and superclusters become, there is a point beyond which the cosmos begins to smooth out statistically. It is clumpy on scales that stagger us, but not infinitely clumpy in every direction forever. That balance matters, because it preserves the strange double nature of the universe, locally structured, globally even. Still, within the range of scales we can meaningfully observe, superclusters are among the grandest recognizable territories matter forms. And yet, they are not quite the oldest structure we have been pursuing. Not in the deepest sense. That is important to keep clear, because the title of this whole journey asks about the oldest structure in the universe, and by now we have traveled from fluctuations to halos, to stars, to galaxies, to clusters, and now to superclusters. It would be easy to assume each larger step is somehow older. But age and size do not always line up the way intuition expects. Superclusters are larger than galaxies and clusters, yes, but they are later expressions of an older pattern. They are descendants, not ancestors. They reveal the slow unfolding of a primordial blueprint, rather than replacing it. In that way, a supercluster is like a mature tree growing from an ancient seed. The tree is larger and more impressive to the eye, but the seed carries the older origin. Still, the tree matters. Superclusters show us what the universe does when its early irregularities are given not millions of years, but billions. They are the broad landscape result of gravity acting across immense territories. They are what happens when not just matter, but whole systems of matter, begin participating in larger arrangements. If you could somehow rise far above a supercluster and see it as a map, you would not see a single glowing object. You would see a region of many galaxy groups and clusters, linked by thinner structures and surrounded by voids so large they would make a normal map feel almost empty. The galaxies themselves would be too small to matter visually at that scale. Even clusters would become points. What would stand out would be the overall shape, the pattern of gathering and separation, the way dense nodes seem to sit along longer strands. And that is why superclusters are such a useful bridge in our story. They teach the mind to stop thinking only in terms of objects and start thinking in terms of patterns. A galaxy is an object. A cluster still feels somewhat object-like. A supercluster begins to feel more like a region in a web. It prepares us for the next step, which is not merely a bigger object again, but the overall architecture of the large-scale universe itself. Before we go there, though, it is worth staying with the emotional meaning of superclusters for a little while. There is something deeply calming about the fact that the universe contains such huge realms of ordered structure, and yet builds them so patiently. No hurry. No single explosive gesture. Just gravity following a blueprint laid down in the earliest moments of time, gathering matter where it can, letting clusters drift into larger domains, letting those domains be shaped by flow, expansion, and the enormous silence of space. Human life feels crowded with urgency. The universe does almost everything that matters without it. Superclusters also give us one more quiet lesson in humility. The Milky Way can feel central when we stand beneath its stars. Our local group can feel significant when we think about its members. Even the Virgo region feels enormous when we first learn of it. But inside structures like Laniakea, all of those familiar names become pieces of a much broader map. We are not in the center of a finished cosmic arrangement. We are in one stream inside one basin inside one vast pattern among many. That does not make us unimportant. It simply makes the universe large in a way our egos cannot flatten. And perhaps that is part of why cosmic scale can be such a good companion for sleep. It does not erase us. It softens us. It places our worries back into proportion. There is relief in being small inside something coherent. Superclusters, in that sense, are not only scientific structures. They are perspective structures. They remind us that the universe's grandeur is not only in bright stars or explosive events. Much of its greatness lies in quiet arrangement, in territories so large that light needs hundreds of millions of years to cross them, and in patterns that only emerge when we step back far enough to stop insisting that meaning must be local. If these slow journeys through the cosmos help you settle in for the night, you can gently support the channel with a quiet like or subscribe. And if you feel like it, leave a comment about where you're listening from tonight. It always feels fitting that many small listeners, scattered across one planet, can gather around the story of how matter gathers across the universe too. For now, though, even superclusters are not the final view. They are vast, but they are still parts of something broader. Once you step back far enough, the provinces themselves begin to connect. Dense regions become nodes. Long bridges of matter stretch between them. Empty voids widen around them. The universe reveals its largest visible design, not as one supercluster or another, but as a web. And in that web, we come closer than ever to the true answer hidden inside the oldest structure of all. Part 8, the cosmic web and the largest pattern we can see. If you keep stepping back from the universe, there comes a point where your idea of structure has to change. A star is easy to picture. A galaxy is harder, but still familiar enough. A galaxy cluster feels enormous, yet it still behaves like a thing you can imagine as a gathering. Even a supercluster, though loose and vast, still sounds like a very large region made of smaller pieces. But if you keep pulling farther away, past individual clusters, past their broad provinces, past the names we give to local territories like Virgo or Laniakea, the universe stops looking like a collection of separate objects. It starts looking like a web. That is not just a poetic description. It is one of the deepest visual truths modern cosmology has uncovered. On the largest observable scales, matter is not spread evenly like mist in a room, and it is not arranged like neat islands sprinkled across a sea. Instead, it forms long filaments, crowded nodes, branching connections, and immense empty voids. Galaxies gather along strands. Clusters sit at intersections. Huge regions between them contain very little at all. The result is a structure so vast that even superclusters begin to look like local features inside something larger. This is what astronomers call the cosmic web. And if you want to understand how big the oldest structure in the universe really is, this is one of the most important places to stop and breathe for a while. Because the cosmic web is not merely one object among others. It is the large-scale architecture of the observable universe itself. It is what happens when the earliest blueprint, laid down in tiny fluctuations near the beginning of time, is given almost 14 billion years to unfold. In a calm way, this is the universe finally showing its full handwriting. The idea can feel abstract at first, because our instincts are trained by the scales we live in. On Earth, structure usually means a mountain, a tree, a building, a coastline, a cloud. Even when we think bigger, we think in terms of planets, stars, or galaxies. But the cosmic web is not a single thing you could point to and say, there it is, complete and self-contained. It is a pattern that emerges only when you step back far enough. It is not a statue. It is a map. And maps ask for a different kind of imagination. If you could somehow rise far beyond the Milky Way, then beyond the local group, then beyond nearby clusters and superclusters, and keep going until individual galaxies became almost too small to matter visually, what you would begin to see is not a smooth fog of matter. You would see lines. Dense, elongated filaments of galaxies and dark matter, crossing space like the strands of some enormous invisible network. At the points where those filaments meet, you would find the richest nodes, the galaxy clusters and crowded cluster complexes. And between those strands, you would see vast voids, regions so empty by cosmic standards that they can stretch across tens or even hundreds of millions of light years. The universe, at its largest visible scales, looks less like scattered dust and more like lace. That image alone is enough to slow the mind down. The cosmic web was not built suddenly. Like every earlier structure in our story, it emerged gradually from the first tiny irregularities in the early universe. Those irregularities were never all the same size or shape. Some existed on smaller scales. Others stretched across much broader regions. Over time, gravity amplified them. Matter flowed toward denser places. Dark matter gathered first, shaping invisible scaffolding. Ordinary matter followed, forming stars, galaxies, and clusters. But because the original pattern had structure on many scales, the result was never going to be a universe made only of isolated clumps. The denser regions connected. The growth of matter was directional. Some places fed into others. Filaments formed. This is one of the most beautiful results of computer simulations in cosmology. When scientists take the early conditions suggested by the cosmic microwave background, add dark matter, gravity, expansion, and the known ingredients of physics, and let the universe evolve inside the simulation, a web appears. Not because someone draws it in by hand, but because it is the natural outcome of matter growing under gravity from those early conditions. The strands, the nodes, the voids, the hierarchy of structure, all of it emerges from the same quiet logic we have been following from the beginning. That matters because it tells us something almost restful. The large-scale universe is not random chaos frozen into accidental shapes. It is intelligible. It has memory. It has inherited its form from a very ancient beginning. The cosmic web is, in a sense, the mature face of the earliest ripples. Of course, the web is not made of visible galaxies alone. In fact, most of its mass is dark matter, just as with halos, galaxies, and clusters. The galaxies are more like lanterns hung along the strands, making the web partially visible to us. They trace the deeper underlying structure. Where galaxies appear in great numbers, it is often because dark matter already built the highway. Where the universe looks empty, it is often because there was never enough underlying density to pull matter together efficiently in the first place. This means the cosmic web is not just a pattern of stars. It is a pattern of gravity made visible. That may be the most important phrase in this whole section. We often imagine the visible universe as the main event, as though whatever shines most brightly must also be the deepest truth. But again and again, cosmology invites us to soften that assumption. The great structures we admire are often only the illuminated edges of something more fundamental. The web is real because gravity shaped it. Galaxies simply help us notice. And the voids matter too. It is easy to focus only on the filaments and clusters because they contain the galaxies, the light, the drama of density. But the voids are just as much a part of the cosmic web as the strands themselves. A web without gaps would not be a web. These voids are some of the emptiest large regions in the universe, places where matter is far more sparse than average. They are not perfectly empty, but compared with the crowded nodes and filaments, they are astonishingly underfilled. Some voids span tens of millions of light years. Some are much larger. If you placed the Milky Way inside one of the great cosmic voids, the night sky of any planet there would look profoundly different. Nearby galaxies would be far fewer. The sense of cosmic loneliness would be stronger. The local universe would feel less crowded, less ornamented, more silent. In that way, the cosmic web is made as much by absence as by presence. This is one reason it feels so visually powerful in maps and simulations. The dense strands matter because the voids make them legible. The nodes look crowded because the emptiness around them is so immense. Structure, in the universe, is often a conversation between what gathers and what does not. There is a philosophical softness in that. Emptiness is not always the opposite of form. Sometimes it is part of what allows form to appear. The cosmic web also changes how we think about distance. When we talk about galaxies, or even clusters, it is tempting to imagine them as separate destinations, each with its own surrounding darkness. But the web teaches us that the universe is not only a set of destinations. It is a system of routes. Matter flowed along these filaments over cosmic time. Galaxies did not simply appear anywhere. They tended to form and migrate within an existing larger pattern. Clusters at the intersections of filaments grew rich because the web fed them. Along these giant strands, matter had a preferred path. So a filament is not just a bridge made of galaxies. It is a history of flow. This is part of why the cosmic web comes so close to answering our original question. When we ask about the oldest structure in the universe, we are really asking about the oldest large-scale pattern that endured and shaped everything that came after it. The web, or at least the primordial blueprint from which the web grew, has a claim unlike almost anything else. It is not merely large. It is foundational. It began as tiny differences in the infant universe, visible in the cosmic microwave background as fluctuations so slight they had to be color-enhanced for us to notice them. Over billions of years, those slight differences became the cosmic web we see traced by galaxies today. So the web is ancient, but not ancient in the same way a fossil is ancient. A fossil is an object left over from the past. The web is the past still unfolding. It is the early blueprint, stretched, matured, and made visible through the long labor of gravity. And in terms of size, it is hard to exaggerate how large the web feels once you try to imagine it properly. Individual filaments can stretch across hundreds of millions of light years. The separations between major voids can be equally staggering. Superclusters occupy portions of the web, not the whole of it. Clusters are nodes inside it. Galaxies are tiny lights inside the nodes and strands. If a galaxy is like a grain of luminous dust, the cosmic web is the pattern that determines where whole drifts of dust will gather across the largest visible territory nature allows. This is where ordinary language starts to strain. Even the phrase hundreds of millions of light years quickly becomes more symbolic than emotional. We hear it, but we do not really feel it. The numbers are too large. So perhaps it helps to say it another way. A beam of light, moving faster than anything else in nature, would need longer than the entire history of complex life on Earth just to cross one great filamentary region of the cosmic web. Entire evolutionary sagas can unfold on one small planet while a photon is still making its way across part of the universe's larger architecture. That is the scale we are standing in now. And yet the cosmic web is not the entire universe in the absolute sense. It is the structure of the observable universe, the part from which light has had time to reach us since the beginning of cosmic expansion. Beyond that horizon, there may be more web, more matter, more vastness. But we cannot see it. So when we talk about the cosmic web, we are talking about the greatest pattern accessible to observation, the largest visible expression of the universe's ancient blueprint. There is something beautifully honest about that limit. Cosmology reaches very far, but it also knows where sight ends. Still, within what we can see, the web is astonishing enough. Astronomers did not discover it all at once. It took generations of surveys, mapping the positions of galaxies across larger and larger regions of space. As the maps improved, the pattern became clearer. Galaxies were not arranged randomly. They lined up in filaments. Clusters occupied intersections. Huge voids opened between them. The more of the universe we mapped, the more coherent the pattern became. Some famous surveys turned these distributions into images that almost look biological, like neural tissue or branching roots or sponge-like tissue seen under a microscope. That resemblance is visually striking, though we should not push the analogy too far. The cosmic web is not alive in the biological sense, but it does share with living systems a kind of networked complexity. It is not a pile. It is an arrangement. And perhaps that is why it can feel so strangely intimate despite its size. Networks are easier for the mind to connect with than pure emptiness. A web suggests relationships, a structure of links, a pattern of belonging. Even in a universe that is overwhelmingly vast, there is something calming about seeing that its largest scales are not just empty spread, but connected form. This is also where the story begins to circle back toward the cosmic microwave background, the oldest light in the universe. In those ancient temperature fluctuations, we can already see the first hint of the density differences that would later grow into the web. Not the finished filaments themselves, not the mature clusters and voids, but the blueprint, the infant pattern, the oldest memory of the structure to come. So in one sense, the cosmic web is old. In another sense, it is younger than its own seed. The web as we map it today is the evolved form. The oldest version of it was only a whisper in the early universe, a slight unevenness in a nearly smooth sea of matter and radiation. But because the pattern endured, because gravity kept building from it, the modern web and the ancient ripple are part of one continuous story. That continuity is what makes the answer to our title question so interesting. The oldest structure in the universe is not best imagined as a single giant object waiting out there somewhere, bigger than all the rest. It is better imagined as a pattern, a set of primordial unvenuses that grew into the largest connected architecture we can observe. The answer is not one island. It is the whole ancient geography. And that geography is still not done surprising us. Because even within the web, there are specific structures so vast that they almost sound implausible when first described. Giant walls of galaxies, enormous filaments, structures so large that they make even superclusters seem local. Some of them have sparked debate about how comfortably they fit with our broader understanding of cosmic scale. Some are still being refined as data improves. but all of them reveal the same thing. The web is not modest. It is capable of building on scales that nearly break intuition. That is where we go next. Before we leave this part, though, it is worth resting for one quiet moment inside the image itself. Picture the universe not as scattered lights, but as a dark expanse with luminous strands running through it. Along those strands, galaxies cluster like dew on fine threads. At the intersections, giant nodes of matter gather thousands of galaxies in crowded regions of gravity and hot gas. Between the strands, voids open like black inland seas, regions so empty they feel almost untouched. And the whole pattern stretches farther than thought can comfortably follow. This is the cosmic web, not a decoration laid on top of the universe, but the universe's large-scale structure itself. The mature expression of ancient ripples. The old blueprint made visible through time. The place where scale stops being about objects and becomes about design. If these slow cosmic journeys help you settle in for sleep, you can gently support the channel with a quiet like or subscribe. And if you feel like it, leave a comment about where you're listening from tonight. There is something calming about many separate people gathering around the story of how the universe itself gathered into a web. For now, though, we are standing at the edge of the biggest patterns most people ever imagine. And even here, the cosmos has one more way to stretch the mind. Because inside this web, there are structures so vast that they feel almost excessive. Great walls, giant filaments, colossal arrangements of galaxies that push our sense of size to its limit. And when we meet them, the question returns with even more force. How big can a structure in the universe really become? Part 9, the Great Walls, the giant arcs, and the structures that almost feel too big. Once you begin to understand the cosmic web, a quiet shift happens in the mind. You stop asking only where things are, and you start asking how far a pattern can go before it stops making sense as one pattern at all. A galaxy is easy to name. A cluster is still easy enough. A supercluster already begins to feel loose around the edges. But then you hear about something called a great wall, or a giant arc, or a structure stretching across more than 1 billion light years, and the old instinct returns. Surely that is too much. Surely the universe cannot really keep organizing matter on scales like that. And yet, it seems that it can. Or at least, it can come surprisingly close. Among the most astonishing things astronomers have found are enormous arrangements of galaxies and galaxy clusters that seem to line up into wall-like, filament-like, or arc-like forms. Some are well established and directly mapped in galaxy surveys. Others are more tentative, inferred from more indirect tracers like quasars or gamma-ray bursts. Some are widely accepted as major features of the cosmic web. Others remain debated, not because they are uninteresting, but because the larger the claimed structure, the more careful science has to be about what counts as real, coherent, and meaningful. NASA science. That caution is important. It keeps the story honest. Because Part 9 is where the universe begins showing off structures so large that even cosmologists sometimes pause and ask whether the pattern is exactly what it first appears to be. Not whether the data are fake, but whether the structure is truly one connected thing, how it should be measured, and what it means for our picture of the cosmos. In a way, this is the point in the story where size becomes philosophical. How large can a structure be and still count as a structure? The most grounded place to begin is with the Great Walls mapped in galaxies themselves. NASA's current overview of large-scale structure describes galactic walls as likely the largest known superstructures within the observable universe, stretching hundreds of millions of light-years across while remaining relatively thin. It highlights the Coma Wall, roughly 500 million light-years long, and especially the Sloan Great Wall, which spans about 1.4 billion light-years. These walls are not solid slabs, of course. They are enormous concentrations of galaxies, groups, and clusters arranged in extended, wall-like patterns within the cosmic web. NASA science. The phrase wall makes them sound flat and architectural, and in a loose visual sense that is fair. But a cosmic wall is really more like a stretched, crowded ridge in the web of matter. Not a brick barrier. Not a smooth plane. More like a giant elongated region where many structures gather close enough that, on the largest maps, they resemble one broad sheet or rampart. There is something deeply soothing about the idea that the universe can build on that scale without any sense of hurry. The Sloan Great Wall, for example, is not one object born in one moment. It is a huge arrangement of galaxy clusters, superclusters, and connecting regions, revealed by large redshift surveys that map where galaxies actually are in three-dimensional space. When astronomers say it spans around 1.4 billion light-years, they are describing one of the largest prominent galaxy-defined wall structures we know of nearby in cosmic terms. It is one of those discoveries that makes a galaxy cluster suddenly feel almost local. NASA science. And the Sloan Great Wall is not alone. In 2020, researchers using the Cosmic Flows mapping effort described another vast nearby structure called the South Pole Wall. According to the University of Hawaii summary of that work, the South Pole Wall lies just beyond Laniakea, extends in an arc of about 200 degrees across the sky, and is as large as the Sloan Great Wall, though much closer to us. One reason it took so long to notice is that parts of it lie behind regions of the sky obscured by dust in our own galaxy, so its presence had to be inferred partly through the motions of galaxies and their gravitational influence. University of Hawaii. That detail is worth lingering with. Even giant structures can hide. Not because they are small, but because our vantage point is limited. We are trying to map the universe from inside one galaxy, through dust, incomplete surveys, selection effects, and the basic challenge of measuring distances across unimaginable scales. There is something comforting in that. The universe is not obligated to be obvious. Sometimes even a structure comparable to the Sloan Great Wall can remain partly concealed until better maps and better methods slowly bring it into view. University of Hawaii. Already, then, we have walls on the scale of roughly 1 billion light-years or more. That is enough to quiet almost any ordinary sense of proportion. But the story does not stop there. In the last few years, several even larger candidate structures have attracted a great deal of attention, especially because they may push against the scale at which the universe is usually expected to look statistically smooth. Among these are the Giant Arc and the Big Ring, both identified using absorption systems in the light of distant quasars rather than simple nearby galaxy counts. The Giant Arc was reported as spanning about 1 gigaparsec, roughly 3 billion light-years in present epoch proper size, while the Big Ring was reported with a diameter of about 400 megaparsecs, roughly 3 billion light-years, and a circumference of about 4 billion light-years. Both were found in the same broad cosmic neighborhood at around the same epoch, which is part of why they attracted so much interest. Auckland, University of Central Lancashire. Now, this is where it becomes important to stay gentle and careful. These ultra-large structures are not fake discoveries. They are serious published results. But they also sit in a part of cosmology where interpretation matters a great deal. The researchers themselves frame them cautiously, as discoveries that may challenge standard expectations about large-scale structure and the cosmological principle if they hold up as physically meaningful structures of the claimed scale. That cautious language is healthy. It is how science protects wonder from turning into oversimplification. Auckland, University of Central Lancashire. In other words, some giant structures are very well established as large galaxy walls. Others are candidate ultra-large structures whose significance is exciting precisely because they may be pushing the limits of what we expect to see. And then there is the most extravagant claim of all. The Hercules Corona Borealis Great Wall has been reported from the clustering of gamma-ray bursts around a redshift of about 2, with an estimated size of roughly 2 to 3 gigaparsecs. That is so large that the numbers almost stop feeling physical. Depending on how you phrase it, you're talking about something on the order of several billion light-years across, occupying a huge fraction of the sky. A later analysis in monthly notices of the Royal Astronomical Society argued that the clustering may indeed be real, but also stressed that its physical nature is still unknown and that better future data would be needed to decide conclusively whether it is truly the largest observable structure in the universe. OUP Academic. That is exactly the kind of scientific sentence I like for this channel. May indeed be real. Still unknown. Need better data. It has humility inside it. Because when the universe starts presenting structures this large, science is right to become more quiet, not less. It is easy to say biggest ever, largest known, impossible scale. It is wiser to say here is what has been reported, here is what seems robust, here is what remains debated, and here is why the debate matters. The debate matters because cosmology expects something subtle on the very largest scales. It expects local clumpiness, yes. Filaments, walls, clusters, voids, certainly. But it also expects that once you average over large enough volumes, the universe should become statistically homogeneous. Not perfectly smooth in every little patch, but smooth enough in the big picture that no single structure should dominate indefinitely. Ultra-large claims become interesting partly because they test where that transition to smoothness really happens, and whether our way of defining a structure is sometimes more complicated than intuition first suggests. OUP Academic. This is one of the most elegant tensions in all of cosmology. The universe is web-like, but not infinitely web-like. It is structured, but not without limit. It is clumpy, but on the biggest scales it is also expected to calm down statistically. So when astronomers find a giant wall, or a giant arc, or a possible gamma-ray burst-defined structure of extraordinary size, they are not simply adding another name to a cosmic atlas. They are testing the grammar of the universe itself. What counts as a sentence in the language of structure? Some of the best-known names in this part of the story are already wonderfully evocative. The Sloan Great Wall, the South Pole Wall, the Giant Arc, the Big Ring, the Hercules Corona Borealis Great Wall. Even before you know what they mean, they sound like things from a dream. And perhaps that is fitting, because they occupy the dreamlike edge of what the mind can comfortably picture. Still, it helps to anchor the imagination with simpler comparisons. A wall a billion light-years long means that light, moving at the fastest speed possible, would take a billion years to cross it. On Earth, during a billion years, continents drift, oceans open and close, mountain chains rise and erode, life reinvents itself again and again. All of that can happen while one beam of light is still making its way from one side of a great wall-like structure to the other. That is the scale at which these names live. And yet, there is another reason these structures matter that has less to do with their size alone. They reveal how the cosmic web can express itself in forms that feel almost familiar to human pattern recognition. Walls, arcs, rings, great lanes of galaxies, long crowded ridges across space. Of course, we should be careful not to imagine literal perfect shapes in the way a child draws a ring or a ruler draws a line. Real cosmic structures are messy. Their edges are fuzzy. Their members are separated by huge voids and gradients in density. But on the largest maps, enough coherence appears that these human names begin to make sense. And that naming, strangely, is part of how we cope with scale. A structure of a billion light-years is too large to feel. But a wall is something the mind already knows. An arc is something the eye already recognizes. A ring is a shape we can carry inward even when the object itself is unimaginably beyond us. There is a tenderness in that. Science uses numbers, but the human mind often needs metaphors to stay close to reality. Another important point is that not all giant structures are equal in the way they are observed. Some are traced directly by large surveys of galaxies. Others are inferred from quasars, absorption systems, or gamma-ray bursts that act like distant beacons. Those methods can reveal structure in epochs and scales where ordinary galaxy mapping is much harder, which is part of why they are so exciting. But they can also make interpretation trickier. Are we seeing one connected overdensity, or a pattern created by the way rare tracers are distributed? Are we measuring a physically coherent structure, or a looser statistical association? These are not reasons to dismiss the discoveries. They are reasons to appreciate how careful cosmology has to be when the claims get truly large. OUP academic. And maybe that carefulness is part of the sleep-friendly beauty here. The universe does not need us to shout about its biggest things. It is enough to notice them slowly, to let the names settle, to understand that some walls are already firmly part of our map, while some ultra-large candidates remain part of an active conversation. To feel, quietly, that even the debate itself is magnificent. Because what a strange and lovely species we are, that we can argue in good faith about whether a structure several billion light-years across is truly one thing or several things gathered into a pattern. That is not ordinary life. That is the mind wandering very far from home. If you step back from all the names for a moment, a simple truth remains. The cosmic web is capable of producing structures so large that galaxies become mere decoration along them. Great concentrations of matter can stretch across distances that make clusters feel small and superclusters feel provincial. Some of these structures are accepted landmarks. Some are candidates at the frontier. Together, they show that the answer to how big structure can get is not small, not modest, and not easily contained by instinct. And yet, even here, we still have to circle back to the deeper question behind the title. Are these walls and arcs the oldest structure in the universe? Not exactly. They are among the largest late-time expressions of the oldest structure. That difference matters. Because a great wall is not primordial in the way the microwave background pattern is primordial. A giant arc is not older than the initial fluctuations that made its existence possible. These immense structures are descendants. They are what the earliest Venuses became after billions of years of gravitational growth. They are majestic, yes. They may be among the largest recognizable patterns we can map, but they are not the seed. They are the branch. And that is where the story prepares itself for its final turn. We began with a seemingly simple question about the oldest structure in the universe. Along the way, we met tiny irregularities, dark matter halos, first stars, first galaxies, groups, clusters, superclusters, the cosmic web, and now these colossal walls and giant candidate structures that almost seem to press against the edges of reason. But the true answer has been quietly waiting behind all of them. Not one wall. Not one arc. Not one cluster of gamma-ray bursts. Not one named object at all. The oldest structure is the original pattern that all of these later forms inherited, the first faint blueprint frozen into the universe when it was young enough that no star had yet existed. So before we end, rest for one moment inside the scale of what we have just crossed. Picture one of these great walls stretching across the dark like a crowded ridge of galaxies and clusters, longer than 1 billion years of light travel. Picture another hidden partly behind dust until motion gave it away. Picture vast candidate arcs and rings, half whispered by quasar light from a younger universe. Picture even the bold possibility of a structure so large it spans billions of light years and still refuses to become simple. And then picture all of them as late echoes of something older. A primordial unevenness. A pattern. A memory. If these slow journeys through the cosmos help you settle into sleep, you can gently support the channel with a quiet like or subscribe. And if you feel like it, leave a comment about where you're listening from tonight. There is something calming about many small listeners, in many distant places, drifting together through the biggest structures the universe has ever shown us. Part 10. How big the oldest structure in the universe really is. By this point, the question has changed shape. At the beginning, it sounded simple, almost like the kind of question you could answer with a single number. How big is the oldest structure in the universe really? It sounds like you are looking for one object, one giant thing floating somewhere out in the dark, larger than all the others. A structure with a name, a place you could circle on a map, something like a galaxy, or a cluster, or one of those enormous walls we just visited. But the longer we stay with the universe, the more it teaches us that its deepest answers are rarely that neat. Because the oldest structure in the universe is not really one object in the familiar sense. It is not one wall, not one arc, not one supercluster, not even one filament of the cosmic web. All of those came later. All of those are descendants. They are beautiful descendants, unimaginably vast and patient, but they are not the first thing. The oldest structure is older than galaxies, older than stars, older than dark skies, older than atoms as we know them. It was already there when the universe was still young enough to glow everywhere at once. And in its earliest form, it was not a thing. It was a pattern. That may sound softer than the title promised, but in truth it is stranger, and much bigger. If we go all the way back to the beginning of our story, to that hot, dense young universe filled with light trapped in glowing plasma, we find something almost perfect in its smoothness. Almost. Not quite. Hidden inside that smoothness were tiny irregularities, the faintest differences in density and temperature, slight ripples in the early cosmos. Those ripples were so small they differed from the average by only about 1 part in 100,000. To the eye, the universe would still have looked astonishingly uniform. But gravity noticed what the eye could not. Those tiny irregularities were the first blueprint. They were the earliest structure, not because they looked impressive, but because they endured. They told matter where to gather a little more easily and where to gather a little less. Over time, they became dark matter halos, then stars, then galaxies, then clusters, then superclusters, then the cosmic web and the giant structures inside it. Everything we have been following since Part 2 was already hiding inside those first slight differences. That means the oldest structure is not best imagined as one late-time cosmic monument. It is the original map from which all monuments grew. And that raises the final question in the clearest way possible. If the oldest structure is this primordial pattern, then how big is it really? There are two beautiful answers. The first answer is that the oldest structure is, in a sense, the entire pattern spread across the whole observable universe. That is the biggest answer, and also the calmest. When we look at the cosmic microwave background, the afterglow of the early universe released when the cosmos became transparent, we are looking at an all-sky map of those first meaningful irregularities. That map surrounds us in every direction. It is not a local object. It is the oldest visible pattern we can observe, stretched across the whole sky, a record of the universe when it was only about 380,000 years old. In that sense, the oldest structure is as large as the observable universe itself. That phrase is so large it barely behaves like language anymore. The observable universe has a diameter of roughly 93 billion light-years. Not because it is only 93 billion years old, of course, but because space has expanded while the ancient light was traveling to us. So when we say the oldest visible structure spans the observable universe, we are saying that the first great pattern of cosmic unevenness is written across a realm tens of billions of light-years wide. That is almost too large to feel. And maybe it helps to say it another way. The oldest visible structure is not somewhere inside the universe like a special landmark. It is woven across the entire ancient sky. Wherever you look, you are looking into part of it. In every direction, the oldest light carries information about that primordial pattern. There is no corner of the observable cosmos where its memory is not present. So if the question is asking for the broadest possible answer, the oldest structure is universe-sized. Not metaphorically. Actually. But there is also a second answer, and this is the answer that feels more like a measuring tape laid gently across the early cosmos. Within the ancient pattern of the early universe, one scale became especially important. It came from those primordial sound waves we visited back in Part 1, the great ripples that moved through the hot plasma before light was finally set free. Those sound waves could only travel for a limited amount of time before the universe became transparent and the pattern froze into place. The maximum distance one of those waves could travel became a kind of standard cosmic scale, often called the sound horizon. In today's expanded universe, that scale is roughly around 490 million light-years across. 500 million light-years. That is a useful number because it gives shape to something otherwise too diffuse to hold in the mind. It tells us that one of the key built-in scales of the oldest observable structure, one of the first giant imprints left in the matter and light of the universe, spans about 500 million light-years today. That alone is already enormous beyond ordinary comprehension. A galaxy like the Milky Way is about 100,000 light-years across. So the sound horizon scale is thousands of times wider than our galaxy. Light could cross the Milky Way in 100,000 years, which is already longer than most of human civilization. To cross one of these primordial scale imprints would take roughly 5,000 times longer. And yet that is still not the biggest possible way to answer the question, because that scale exists inside the larger ancient pattern spread across the whole observable universe. So perhaps the gentlest way to put it is this. The oldest structure in the universe has a characteristic scale of roughly 500 million light-years, but its full pattern extends across the entire observable cosmos. Both are true. One answer gives us the size of a major built-in feature. The other gives us the size of the whole ancient design. And when you hold those two truths together, the question becomes wonderfully strange. The oldest structure is both immense in its pieces and universe-wide in its reach. It is at once a set of giant primordial ripples and the complete all-sky map they form together. This is why the later structures we talked about, the giant walls, the Sloan Great Wall, the South Pole Wall, the great filaments and broad supercluster domains, feel so impressive and yet somehow secondary. Some of them are larger in one direction than the sound horizon scale. Some stretch across more than 1 billion light-years. Some may reach far beyond that, depending on how one defines them. But they are later elaborations. They are the mature architecture of matter after billions of years of growth. The primordial pattern is older than all of them. It is the original sentence before the long paragraph of cosmic history was written. And there is another quiet reason this answer matters. It changes what we mean by structure. We usually think of a structure as something assembled, like a building or a skeleton or a mountain range. Something with a shape you can walk around in your mind. But the universe asks for a wider definition. In cosmology, structure can begin as statistical unevenness, a field of slight preference, a pattern of denser and less dense regions. It does not need solid edges to be real. It only needs the power to guide what comes next. By that standard, the primordial fluctuations recorded in the cosmic microwave background are absolutely a structure. In fact, they are the most ancient one we can still observe directly. And perhaps that is why they feel so haunting. When we look at a galaxy, we see a mature thing. Beautiful, yes, but already far along in its history. When we look at the cosmic microwave background, we are not looking at maturity. We are looking at infancy. We are seeing the universe before its first stars, before its first galaxies, before chemistry became rich, before the night sky learned how to shine in the way we now know it. We are looking at pure potential, arranged into the first discernible pattern. That makes the oldest structure not only the largest ancient design, but also the oldest visible memory. There is something deeply peaceful in that phrase. The universe has a memory, and it is written in light. Not the bright visible light of stars, but the faint microwave afterglow of a time when the whole cosmos was young and nearly smooth. That memory is still here. It fills space. It passes through us constantly. It arrives from every direction, carrying the image of the universe before structure became dramatic. And inside that light, the ancient pattern still remains. This is one of the most comforting things astronomy can offer. The universe did not lose its beginning entirely. It kept a record. It allowed one very old signal to survive. So even though the first stars died long ago, and galaxies merged, and clusters grew, and walls of matter stretched across the web, the early pattern still exists as a kind of background truth beneath all later history. The oldest structure did not disappear. It simply became the foundation under everything else. You could almost think of the universe as a cathedral built from an old set of faint lines drawn on paper. Over time the walls rise, towers appear, windows take shape, and people walking through the finished building may admire the later grandeur. But if you could somehow see through the stone and glass, back to the original marks on the blueprint, you would discover the first design that made all the rest possible. The cosmic microwave background is that blueprint still faintly visible through the finished building of the cosmos. And because we are bringing the whole story to a close, it is worth retracing the path one last time, slowly. First there was a nearly smooth universe, hot and bright, but with tiny irregularities already present. Then those irregularities became the seeds of gathering. Dark matter formed halos, invisible wells in the cosmic landscape. Gas fell into those wells. The first stars ignited. The first galaxies slowly assembled. Galaxies gathered into groups and clusters. Clusters belonged to broader supercluster regions. The cosmic web emerged in full, with its nodes, filaments, and voids. And within that web, giant walls and structures appeared, some of them so large they almost feel like exaggerations spoken by the universe just to test our humility. But beneath all of them, before all of them, and quietly inside all of them, there remained the ancient pattern. That is the oldest structure. Not one named object, not one colossal wall, but the first great arrangement of matter and energy itself. And maybe this is the most important final truth. The oldest structure in the universe is also, in a profound sense, the one we belong to most directly. You are not merely living inside a galaxy that emerged from some later chapter of cosmic history. The atoms in your body, the Earth beneath you, the star that warms this planet, the Milky Way around that star, the local group around that galaxy, and the larger structures beyond all of them were shaped by the earliest blueprint in the universe. The first pattern did not just lead to distant clusters or beautiful walls of galaxies. It led, eventually, to you. There is a direct line, however delicate, between those early ripples and the existence of human thought. That may be the strangest answer of all. The oldest structure in the universe is not only something we observe from a distance. It is something whose consequences we embody. Every star was formed because matter gathered. Every gathering happened because slight unevenness gave gravity something to work with. Every heavy element in your body was forged in stars born inside structures that descended from those primordial ripples. So when we ask how big the oldest structure is, we can say it spans the observable universe. We can say its characteristic early scale is about 500 million light-years. We can say it is larger than any galaxy, older than any wall, and more fundamental than the cosmic web in its mature form. But we can also say something quieter. It is big enough to contain the long cause of everything. Big enough to begin the chain that led from plasma to people. Big enough that you are not outside it, studying it, but inside its consequence. And perhaps that is why cosmic scale can calm the mind instead of only overwhelming it. At first it seems to make us small in a harsh way. But if you stay with it long enough, it starts making us small in a gentler way. Not irrelevant, just connected. Part of a design so old and patient that our individual worries begin to soften at the edges. The universe was not built in chaos alone. It began with quiet structure, almost invisible, almost negligible, and from that near silence everything else slowly grew. That is a very restful thought, because it suggests that not everything meaningful begins loudly. Not everything important begins as an obvious event. Sometimes the oldest and deepest structures begin as subtle differences in an otherwise calm field. A slight unevenness, a hidden preference, a pattern that only reveals its significance after immense stretches of time. The cosmos itself began that way. And maybe that is why it feels fitting to end here, not with the loudest object or the biggest named wall, but with the oldest pattern, the first memory, the faint ripples in the young universe that became all later grandeur. So, how big is the oldest structure in the universe really? It is, in its full visible pattern, as large as the observable universe. And in one of its most important built-in scales, it is about 500 million light-years wide. But perhaps the truest answer is this. It is big enough that everything you know grew out of it. If you enjoyed drifting through this quiet journey into the earliest architecture of the cosmos, you can gently support the channel with a like or subscribe. And if you feel like it, leave a comment sharing where in the world you're listening from tonight. There is something beautiful about many small listeners, scattered across one planet, gathering around the memory of the universe's first pattern. And now, as the universe grows calm again around us, you can let the scale of it soften into the background, not as a problem to solve, just as something old, vast, and quietly beautiful to rest inside.